Hi everybody. Are we back? Yes guys, can you all see me? Yeah, this is the new link, so quickly go and call up your friends. Quickly go and call up your friends. I do not know why the last one stopped suddenly out of nowhere. I mean, my internet was also working, OBS was also working fine, but there was something that went wrong. Yes, I can see that many of the students are coming. So I'm not going to waste too much time, guys. Let us quickly start with the session. Okay? Have you eaten? No, bacha, I haven't eaten. I haven't eaten anything since morning. Just had one medicine, that was Saridon, to stop my running nose. Yes, everybody quickly go and call up your friends. I'm going to wait for 2-3 minutes. Just 2-3 minutes. Okay, Azan, no problem. Yes, no problem. Yes. Shall we start? Shall we start? Okay. So as I was showing you, what was I showing you? I was telling you that this is how the f orbitals are going to shield, right? The f orbitals will be shielding like this. What is the point of shielding when the nucleus is directly able to see? So if I have a, if I have a scarf like this, does it even matter? It doesn't matter. It doesn't matter at all because you can crystal clearly see my face. So that is why when the lanthanoids are apart, the moment the f orbitals are a part of the electronic configuration, them being the worst kind of shielders, the nucleus can see through them, they can look at the last electron and they can pull the last electron towards themselves. Hence the atomic radius, there is a very, there is a very consecutive decrease in the sizes of the atom the moment the lanthanoids are a part of the are a part of the what do you say, they become a part of the orbitals, right? So that is called as a lanthanoid contraction. Okay, that is what is called as a lanthanoid contraction. When did I tell you, Balaji, that 2:30 is the ending of the session? Did I by any chance ever tell you that 2:30 is the time of the session? I did not give you any end session. I did not give you any end time of the session. Constantly, why you guys are sitting on my head and talking about this, ma'am? Will you be able to end it? Will you be able to end it? I gave you one whole day for inorganic and physical chemistry, right? So the question should be, by 10 o'clock tonight, will we be able to finish? Yes, we will be able to. Stop asking this question again and again. You are supposed to write the answer. I am the one who is sacrificing. I can't understand that. What is wrong with you all? And why can't you understand? And now you are saying, okay, chill. Wah. I'm supposed to chill. Since morning, from the time I started to take the class, I'm telling you that chill, we will finish. Chill, we will finish. No chill. You have zero chill at all. Kept telling you that I did not even have my breakfast because I was making the slides. I was collecting the previous year question and everything. And you guys are sitting on my head and asking, ma'am, will we be able to finish? Will we be able to finish? Ma'am, when are we going to do this? When are we going to do that? Leave it up to the teacher, no? The teacher is taking the class, right? और ये देखो एक और आ गया है, मैराथन नो टॉर्टोवाइस रेस. मत पढ़ना फिर, मत पढ़. Why are you studying from here? Go read it from somewhere where they are doing it in 30 minutes and see if you get better marks or these students they get better marks. Okay, so once again everybody, what is lanthanoid contraction? Yes, so we all know that the s orbitals, they can shield the last electrons from the nucleus very well. The p orbitals, they are slightly worse kind of a, they are slightly worse kind of shielders. The d orbitals are even worse and the f orbitals are the absolutely worst kind of shielders. So the moment you see that the f orbitals are a part of the electronic configuration, that means that the nucleus can look at the electron and it can pull the electron closer to it. The shielding is basically not there. Yes, in case of the s orbital and the p orbital, the shielding is there. In case of d orbital and f orbital, the shielding is negligible. That means the nucleus can look at the electron and they can pull it. Hence what happens? The size decreases. And the moment the lanthanoids and the actinoids are a part of the D block elements, that means that the 4f and the 5f orbitals are a part of the electronic configuration. The moment they become a part of the electronic configuration, what happens? There is a contraction. The size of the atom reduces, and that is why we call this to be lanthanoid contraction, everybody. Yes, do we understand, guys? Do we understand, guys? Yes, everybody, do we understand this? Very good. Yes. So which essentially compensates for the expected increase in atomic size with increasing atomic number, and the net result of the lanthanoid contraction is that the second and the third D series exhibit similar radii. That is, you will see that zirconium and hafnium, see, zirconium has 160 picometer, hafnium has 159 picometer, yes, and have very similar physical and chemical properties. Much more than that is expected on the basis of usual family relationship. Usually in the family, you expect that the elements, they will have much different physical and chemical properties. However, when it comes to zirconium and hafnium, niobium and tantalum, molybdenum and technetium, I guess, no. Yeah, molybdenum, and after that, what is it? I have forgotten. Wait. Molybdenum and tungsten. Yes. So molybdenum and tungsten. Everybody, have a look. See. Niobium and tantalum, zirconium and hafnium, molybdenum and tungsten, technetium and rhenium, Ru and Os, that is osmium. Yes. Ruthenium and osmium. These guys, their atomic sizes are very comparable, as you can see. Do you see here? Their atomic sizes are very comparable. See, atomic sizes are very, very, very comparable. Why? Because of lanthanoid contraction. Yes, because of lanthanoid contraction, this happens. Are we clear, everybody? Are we clear, everybody? Very good, very good, very good, very good, very good. Okay, all right, yes. Now what happens? Okay, now what happens? The factor that is responsible for this lanthanoid contraction is similar to that is observed in an ordinary transition series, and it is attributed to similar cause. The imperfect shielding of one electron by another in the same set of orbitals, that is your basically lanthanoid contraction. The 4f orbitals, the 5f orbitals, they have very imperfect shielding. That is why the size of the atom reduces. Okay? Alright. However, the shielding of one 4f electron by another is less than that of one d electron by another. Basically, that is what they are saying. Obviously, the 4f electron will not be able to shield another 4f electron. But a d electron will be able to shield better than the 4f electron. Right? Everyone. Right? Isn't it? Absolutely. Absolutely, guys. Absolutely. Okay? Alright. Now what happens is, see. And as the nuclear charge increases along the series, there is fairly regular decrease in the size of the entire 4f orbital. Because the nuclear charge is increasing. I just told you, there are two factors that affect the atomic radius. One is nuclear charge and one is shielding effect. Because the nuclear charge is increasing, you see that slowly and gradually the atomic size is decreasing even more. Clear hai? Clear, everybody? Yes, can't understand. What is it that you can't understand, guys? What is it that you can't understand? Are you guys understanding what is lanthanoid contraction? Have you all understood what is lanthanoid contraction? Have you all understood what this sentence, this paragraph is trying to say? Huh? Have you all understood? Who is it who is not able to understand? No, not understood. How many of you did not understand lanthanoid contraction? Sachin, looks like you are the only one who did not understand. Can you watch the session again? Can you just rewind it a little bit and understand? Shaji did not understand. Avengers did not understand. Senthil did not understand. I can't understand the whole chapter. Wah, wah, wah. Very nice. Okay. Chalo, once again, let's understand. Guys, S block orbitals. See, this is how I'm shielding my face. Shield. Captain America has a shield, no? Whenever he is fighting, Captain America has a shield, right? You guys have you seen? Captain America has a shield, right? Have you seen that Captain America has a shield or not? Now, I can't understand. Yeah, nobody can understand. You have seen? Captain America has a shield, right? I'll show you. Have you seen? This is called as a shield. This is a shield, right? What does he do? Every time somebody tries to attack him, he gives this shield, right? Like, it goes away, isn't it? Yes. What does he do? He protects himself. He protects himself, isn't it? He protects himself. So now, let's say that I don't want to see the comments, okay? I don't want to see the comments. So what am I going to do? I'm going to shield my eyes like this. Can you see my face? Can you see my face? Can you see my face, guys? You cannot see my face, right? Can you see my face? You cannot see my face, right? You guys cannot see my face right now, isn't it? Yes, you guys cannot see my face. Very good. Now, if I tell you that there is, so this is how the S block can shield. So what happens, let's say that we have an atom. This is the nucleus of the atom. Here you have a S electron, okay? Here you have S block, S orbital. You have here S orbital, okay? And let's say that right here you have a nucleus. So this S orbital, this is going to shield this electron like this, okay? But if, let's say that if we had a P block, if we had a P orbital, then the P orbital is going to shield like this. The P orbital is going to shield like this. Do you guys know the shape of the orbitals, guys? The shape will be even better. See, the S block has a shape like this. The S orbital has a shape like this. The P orbital, they have a shape like this, right? So if this is the, let's say that here is the nucleus and the electron is somewhere here. The nucleus will be able to see the electron, right? This nucleus right here, it will be able to see the electron. Will it be able to pull the electron, right? It can pull the electron. It has pulled the electron. Now, what do you know about d orbital? See, the d orbital, everybody, how does the d orbital look like? The d orbital looks like this, this, and this, isn't it? That means that the electron can be observed from here, can be observed from here, can be observed from here, can be observed from here. There are more places for the electron to come in touch with the nucleus, right? 1, 2, 3, 4, 4 places. 4 places, everybody. Yes? But here, if the electron is here, the nucleus won't be able to see because the S orbital is protecting the electron. But here, there are 4 places. So what happens? The nucleus can pull the electron and the size decreases. The F orbital has even more space. The F orbital can clearly let you see through. So what happens? It gets reduced even more. Now, because where are the F orbitals in place? When do you see the F orbitals coming into picture? During the lanthanum actinum. The moment the lanthanoids start, that means that the F orbitals are apart. That means that the inner transition is now a part of the transition element, right? Right, everybody? Exactly. So the moment you have the lutetium, cerium, lawrencium, europium, dysprosium, ytterbium, yes, gadolinium, all of these, whenever they are there, the electrons are easily visible to the nucleus. The nucleus can do ka-chang and pull the electron. The size reduces. That is called as lanthanoid contraction. Am I clear now, guys? Am I clear now? Yes, guys? Okay, now we are going to move on, and because of this lanthanoid contraction, okay, now everybody, if you look at the periodic table, I think you will be able to understand this better. See what happens here. See. Here, right at this place, guys, here is your lanthanum, here is your actinum. The moment lanthanum and actinum are here, that means you know that the whole F block, they are all a part of this group. Right, everyone? In the periodic table, the whole F orbital, the whole F block element, that is lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Yes, apart from that, here thorium, protactinium, uranium, neptunium, plutonium, all of them, they belong to this group 3. So the moment they are present, what happens here? Hafnium, zirconium, they have comparative sizes. Okay, niobium, tantalum, comparative sizes. Molybdenum, tungsten, comparative sizes. Technetium and rhenium, comparative sizes. Okay, ruthenium, osmium, comparative sizes. Are you getting it? What is the reason? The reason is lanthanoid contraction. Yes, the what is it? The reason is lanthanoid contraction. Do you guys understand, everybody? Yes, do we understand all of these, everyone? Yes, we do. Yes, we do. No, we don't. What is the answer? Do we understand this, everybody? Yes, do we understand this, guys? Yes? Okay. Now, the decrease in metallic radius coupled with increase in atomic mass results in a general increase in the density of these elements. And that is why from titanium to copper, the significant increase in the density may be noted. Okay? The significant increase in the density may be noted. So now let us take a look at this table, guys. These tables are very important. From here, many questions can be seen, everybody. Okay? Many questions will be noticed from this table. You will see. I will give you the PYQs now you will see. Okay? So atomic number for scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Is this clear to you all, everybody? Do you all know, everyone? Do you all know the electronic configuration of scandium to zinc, everybody? Atomic number of scandium to zinc, everyone? Do you all know? Do you all know or you don't? Yeah? Yeah. This is clear? Scandium has an atomic number of 21. See, right here, all the atomic number is given. Okay? Right here, all the atomic number is given. I suggest everybody, if you do not know the atomic number, at least for the first 3D series, learn it. Learn it. It is going to be very important. If you do not know, it is going to be very important, because in the exam they will ask you about it. So it's very important that you learn it. Okay? Now, see, here the electronic configuration they are showing for M+, M2+, and M3+. M3+ means 3 electrons they have given up. 2+ means 2 electrons are given up. M+ means 1 electron is given away, and then what is the electronic configuration, that also they have written. Okay. Enthalpy of atomization, we see that for scandium it is very low, 326 only. For titanium it is slightly higher, 473. And as you go as you move on, you see that for vanadium the enthalpy of atomization is much more, it is 515. For chromium, it has reduced. For manganese, it is even less. Manganese, there is a very good drop in manganese's enthalpy of atomization. Okay? Then we come to ionization enthalpy. Guys, do we all know what is ionization enthalpy? What is ionization enthalpy, my dear bachos? Ionization enthalpy is basically when there is energy required to give away 1 electron from the atom, That is called as ionization enthalpy. Okay, that is called as ionization enthalpy. So here you see for scandium it is very less. The first ionization enthalpy is very less. And as you move ahead, you see that for manganese the first ionization enthalpy is very less. Okay, but what happens is for manganese, the second ionization enthalpy is lesser than that of chromium, guys. Why so? Because chromium will have 3d5 electronic configuration after you have taken away one electron, guys. Yes? Alright, everybody. Alright, everybody. Chalo, once again, let me tell you guys. See, chromium has an electronic configuration of 3d5 4s1. If you take away one electron, it will be 3d5. Okay, now if you want to take away a second electron, it has a half-filled stability, guys. It has half-filled stability. That means that it is very, very, very stable and it does not want to give away the second electron, which is why they have a higher second ionization enthalpy. But in case of manganese, if you see, manganese has an atomic has an electronic configuration of 3d5 and 4s2. Am I right? So if you take away one electron, then it will become 3d5 4s1. Am I right? If you want to take away the second electron, after the second electron, it will come to 3d5, isn't it? So it can easily give away this electron because then it is going to get the half-filled stability and it will be very happy, right? So so do you understand? Do you understand why the second ionization enthalpy of chromium is higher than manganese, guys? Do you understand, everybody? Do you understand? Yes. Do you understand, everybody? Very good. Everybody, please understand, enthalpy of atomization is the energy required to make just one atom. Make isolated atom, an atom that is alone. It is not forming a bond. That is enthalpy of atomization. Ionization enthalpy is from an atom. How much energy do you have to give to take away one electron? Understanding? Understanding? Yes, that is the difference. Okay, that is the difference here. Chalo, guys, moving on. Yes, then when we go to, then as you move forward, you see that yes, the ionization enthalpy that keeps increasing, and in fact for zinc it is much higher because zinc has a stable electronic configuration, right? Zinc has a stable, fully filled electronic configuration, 3d10 4s2. Does not want to mess up with its stability. Zinc is stable. Zinc does not want to give away its electron at all. That is why ionization enthalpy is very, very, very high for zinc. Okay, when you compare it with other elements of the same series. Do we understand? Very good. Now, let us go to metallic ionic radii. So metallic ionic radii also we see that as we move this side, as we move from left to right in the periodic table, in the D block, there is an irregular trend. Okay, there is an irregular trend, everybody. How so? How is this an irregular trend, everyone? See, in case of scandium, it is 164 picometer. Then as soon as you go to titanium, it is 147 for vanadium, 135 for chromium, it is 129 for manganese, it has increased, 137. For iron, again it has decreased to 126. For cobalt, it is 125. For nickel, it is 125. For copper, there is a slight increase in 125. But from here to here, from iron to copper, do you see that the atomic radii or the metallic radii, it almost stays the same? Why so? Because here the shielding effect and the nuclear charge both are dictating the atomic radii equally. Both of them are contributing to the atomic radii and they get compensated, which is why there is not much of an increase in the atomic radii or decrease in the atomic radii. So whenever you come here, you see that there is a slight decrease in the atomic radii. Why so? Because nuclear charge is increasing, but here nuclear charge and shielding effect both are increasing, both are compensating for the atomic radii, hence there is not much of an increase or decrease? Then as you go to zinc, what happens? The shielding effect becomes more. That is why there is a increase in the atomic radii. Everybody, do we understand this? Very good. Okay. Then we come across standard electrode potential. What is standard electrode potential, guys? Everybody, do we all know what is standard electrode potential? Chalo, we will come to standard electrode potential in a while. But density. Density, everybody, you will see that yes, it increases when it comes to cobalt, nickel and copper. It has increased way too much. And as you move from left to right, yes, the density increases. Okay. Yes, the density increases when it comes to the same group as you move from left to right. Okay. But coming back to the standard electrode potential, everybody, let us understand the standard electrode potential. Okay. See, standard electrode potential basically means that from the metal, it has to go to M2 plus in its aqueous form, right? Yes, right, everybody? No. It has to go from, from M2 plus to M. This is what is your electrode potential. This is what is your standard electrode potential, right, everybody? So now everyone, check it out. Do you think that it is as simple as just taking away 2 electrons and converting it into the solid form? No. First of all, what will happen is this metal, it will lose 2 electrons and it will form M2 plus, right? That means that here you will be required to give 2 ionization enthalpy. In fact, even before you give it to ionization enthalpy, first thing that you have to do is you have to change this to gaseous state. That means that you will have to give delta sublimation energy. Okay. First it will go to gaseous state. Once it has gone to isolated gaseous state, then you are going to give it to ionization enthalpy 1 and ionization enthalpy 2. Then it will go to M2 plus because 2 electrons now you have taken away. Okay. 2 electrons you have taken away and then it has reached M2 plus. But right now it is still in gaseous state. Now you have to convert it to aqueous state. Okay. M2 plus aqueous state. How will you do it? You will have to give it delta H hydration enthalpy, guys. So see, there are 1, 2, 3 steps. In fact, 4 steps because you also have to give ionization enthalpy 2, right? So there are 4 steps that is required. Now, certain elements, they want to remain in their own state. Yes. For example, copper. Copper cannot stay in, copper cannot give away just 1 electron. No, copper usually exists as Cu2 plus. And that question is very important in your board. So all the students who are telling that, ma'am, you are so slow. Ma'am, I'm going. She's taking 40 minutes in one page. Go. These important questions, I do not think anybody will tell you the answer. You have less time. No, go study from somewhere else. Go study from somewhere else. All these things that you are writing, this is a very important question that they will ask, that why copper plus is not so stable. Copper 2 plus is very stable. Why? Because once you have given copper just ionization enthalpy 1, the hydration enthalpy is so high that it is not compensated. This does not allow this to happen, or this does not allow that to happen. But when you have taken away 2 electrons, now the copper ion is very small in its state. It is very small. The hydration enthalpy is huge. The ionization enthalpy, the second ionization enthalpy that you gave, that was also huge. So together, this can very well stabilize, and that is why copper 2 plus ions can exist. Copper plus ions cannot exist. And this is the reason. The reason is standard electrode potential. Yes, this reason is standard electrode potential. Now guys, let us come to this question. This is in text question, everybody. Why do the transition element exhibit higher enthalpies of atomization? Because of large number of unpaired electrons in their atoms. They have stronger interatomic interaction and they have stronger bonding between atoms, resulting in higher enthalpies of atomization. The question here is, in the series scandium scandium Z21 to Zn, that is 30, the enthalpy of atomization of zinc is the lowest, that is 126 electron. Okay, zinc does not have unpaired electron. That is why I'm not gonna explain again, guys. You all were busy talking, right? Talk. Talk now. Keep talking. This is your punishment. I'm not going to respond now. See, if I repeat, then you're going to say that, ma'am, you're very slow. If I don't repeat, then you're going to say that, ma'am, you are... So I anyway cannot make you guys happy. And if I answer you like this, then you're going to tell me that, ma'am, you are very rude, even though I'm smiling. You will not understand. So let it be. I don't think I can make you all happy. I'm going to teach. Those who want to learn, learn. If you don't want to learn, chill. Okay? All right, everybody. Yeah. Very good. Kim, very, very, very good. Okay? All right, everybody. Now, moving on, guys. Let us understand ionization enthalpy. Okay? So, let us have a look at the ionization enthalpy. Here it is. There is an increase in ionization enthalpy along each series of the transition elements from left to right because there is an increase in nuclear charge. Yes, because there is an increase in nuclear charge. The number of atomic number is increasing. Atomic number increases, that means protons are increasing. If protons are increasing, that means more positive charge, and that can pull the electron. If they pull the electron, then it is going to be difficult to take away the electron, right? Yes. Try and understand this better. See, if I hold on the book like this, you can easily take it, right? If I hold on to the book like this, like just like this, if I hold on, you can easily take the book. But if I hold on to the book like this, now will you be able to take it? It will be very difficult, isn't it? So if the nuclear charge increases, this is how the nucleus is holding on to the electron, and they do not allow taking away of the electron very easily, which is why ionization enthalpy increases. So understand it this way. If I hold on to the book like this, you can easily take away, right? You can easily take away the book. That means ionization enthalpy is less. But if I hold on to the book like this, then what will happen? You will have to struggle with me to take away the book, isn't it? That means ionization enthalpy has increased, everybody. Do we understand this? Yes, we do. Yes, we do. Okay. All right. So now, Table 8.2 gives the values of first three ionization enthalpies of the first series of the transition elements that we have just seen, right? These values show that successive enthalpies of this element, they do not increase as steeply as in the case of non-transition element. Now, in case of S block elements and in case of P block element, we see that they are non-transition elements and the values, they increase very steeply. But here that does not happen. Why does it not happen? Why does it not happen? Yes. So, it does not happen because these values, see. The variation in ionization enthalpy along a series of transition element is much less in comparison to the variation along a period of non-transition element. The first ionization enthalpy in general increases, but the magnitude of the increase in the second and third ionization enthalpies for the successive element is much higher along a series. Why so? Because what are we doing? Once you have taken away, see, okay, let us try to understand this, okay? Let us try to understand this. See. Today, if you try and make me angry in the chat once, yes, I'll be angry. I'll be angry. And then what will happen? You guys will scold me. You'll be like, ma'am, ma'am, we don't like you, ma'am. You are so rude, ma'am. You get angry all the time. We don't like you. Right? You will go away from the class. Second time, I'll be more careful. Second time, when you try and make me angry, I'll be like, no, I cannot be angry. Right? It will take you more time to make me angry. Third time, it will be even more difficult to make me angry because now I have gotten used to it and I don't want to be angry because I know that if I am angry, then what happens? My classes get affected. Right, everybody? Right, everybody? So, do you understand here? Do you understand here that what is happening? So, initially, when you take away one electron from the atom is like, Arey, what just happened? Somebody took away my one electron. The atom will be like, okay, okay. Let it go. Second time, when there is another electron that you are taking, the atom will be like, oh, this has happened to me previously also. I am not letting my electrons go. I am not letting my electrons go. It will try to hold on. So you will require a little more energy to take away that electron. Third time, the atom will be like, you have come again? Huh? You think that I will just give you electrons free of cost or what? So now the ionization enthalpy will be even more. You will have to really give a lot of energy to take away the electron. Got it? Understand, everybody? Yes, guys. Shall we move on? Let us move on. Okay? Chalo. Now, the irregular trend in the first ionization enthalpy of the metals of 3D series, though all of little chemical significance, and this can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3D orbitals. That is exactly what I said. The moment you take away one electron, what happens? Now the 4s and 3D, they have even better comparable energy, right? Now both of them are trying to make the atom stable. Both of them, both 4s and 3D, they're like, okay, we have to work together and make the atom stable, right? So what happens, the moment you take away one electron, they get very, very, very flustered that atom stability, what to do. Both of them are going to take part exactly equally to make sure that the atom is stable. Okay, they are going to try and make the atom stable. So the moment you take away one electron, there is a slight change. There is a, actually not slight, there is a major change in the dynamics of the 4s and 3D, and that is why this happens. Okay, that is why this happens. All right, everybody. Yes, guys. Okay, chalo. Moving on, everyone. Moving on here from here. Yes. Then what happens? Now you have learned that when d block elements form ions, ns electrons are lost before n-1 d electrons. So first, what happens whenever you want to take away an electron, you usually generally take it from the 4s electron. You do not take it away from the d orbitals. You take it from the s orbital first, right? That is what they are telling you here. Now, these 3d orbitals shield the 4s electron from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another, right? Therefore, the atomic radii decreases less rapidly, and thus ionization energies increases only slightly along the 3d series. The doubly or more highly charged ions having a dn configuration with no 4s electrons. Yes, what happens is, whenever there is only d electrons, the doubly or more highly charged ions have configuration with no 4s electron. Yes, everybody, are you guys getting it? Abhay? Yeah, seriously. Rupa, thank you so much. Thank you so much. Yes, please tell me, why are you guys not studying? My God. Seriously, it's so messed up. So messed up, guys. You guys don't have exam or what, huh? Anyway, chalo, moving on, everybody. Do we understand this paragraph, guys? Yes, all the students, those who are studying. Yes, Nitish, Krishna, Kavi, Rupa. Guys, it will take me some time to disable the chat and all. It's a lot of, task. So those of you who are studying, I'm only talking to you. Rest, other students, I am not even talking to them. Please tell me that, are you guys understanding? Are you guys with me, those who are studying? Our pigeon friends, no, stay here. I'm teaching you, right? It will be easier for you. Imagine that this is like a... Are we back, guys? Yeah, there was a slight lag. Now is it fine? No. Please, don't say that. Don't say that. You are understanding. Great. Yes. No, I cannot disable the chat because then those who are studying, they will not be able to ask their doubts, right? I need to know your doubts at least. Chalo, guys. Moving on. Okay. Once again, everybody, have a look. So what happens is, these 3D electrons, they shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield another. That means, what is this line saying? This line is saying that the 3D electrons, that is 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, yes, these electrons, they can shield the 4s electrons better. When one electron goes away from 4s electron, now the 3D is going to shield the last electrons better. That is why the ionization enthalpy increases. Okay? Alright. But if there were 2 electrons in the 4s orbital, then the 2 electrons, they are not able to shield it better. Okay? All right, everybody. Yes, explaining. Abhimanyu, again explaining, bacha. Again explaining. See? Again explaining. Yeah. Okay? All right, yes. Now what happens is, therefore, the atomic radii decreases less rapidly. Because now the 3D is shielding better, the atomic radii is not decreasing very fast. That means what did I tell you? The nuclear charge and the shielding effect, they were what they were doing? They were balancing each other. Yes, they were balancing each other. That is why. Okay? Alright, now therefore the atomic radii decreases less rapidly, thus ionization energies increase only slightly along the 3D series. The doubly or more highly charged ions have DN configuration with no 4s electron. For example, guys, tell me, what is going to be Mn plus 3? Mn plus 3 electronic configuration will be what? Usually Mn has 3d5 4s2. If you take away 3 electron, it is going to have 3d4, right? There are no 4s electron. Are there any 4s electron here? Do you see any 4s electron? None. Exactly what is meant by this. Exactly what is meant by this sentence here. This sentence. The doubly or more highly ions have DN configuration with no 4s electron. Do you get it? Do you get it? Do you get it? Yes. Now, a general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases, because one d electron does not shield another electron from the influence of nuclear charge, because d orbitals differ in direction. Remember, I just showed you how the d orbitals are. How do the d orbitals look like, guys? The d orbitals, they look like this, and this. All of them have different directions. So they are not able to shield the last electrons. Hence what happens? Ionization enthalpy increases. Okay, ionization enthalpy increases. Very good. Okay, now what happens, guys? Now moving on from here, everybody see. The trend of steady increase in second and third ionization enthalpy breaks for the formation of Mn2 plus and Fe3 plus respectively. In both the cases, ions have D5 configuration. Similar breaks occur at corresponding elements in the later transition series. Acha. Now, this question may come, everybody. Please pay attention, everybody. Look at me. Look at me. Look at me. Look at me, everybody. Focus up, everybody. Focus up, everyone. This question may definitely come in your exam. The question is that Mn2 plus and here you have Fe3 plus. Okay, what happens to their ionization enthalpy? Have a look, everybody. Have a look. See. Have a look, everybody. Have a look. See. Mn2 plus has an ionization enthalpy of 1509. Okay, but Fe3 plus has a very less, ionization enthalpy, which is only 2962. But see here, 3260. See, 3260. Guys, do you see? 3260 and 2962. There is a decrease. Why? Okay. Now, everybody, let us come to electronic configuration. Manganese. If you take away 2 electrons from manganese, it will be 3d5, right? If you take away 3 electrons from iron, if you take away 3 electron, what will it give you? It will give you 3d5. That means that when you take away the third electron from iron is readily it is agreeing to give you the third electron, because it will attain the half-filled stability. Getting my point, everybody? Are we getting my point, everyone? What did I tell you? Once again, everyone. Okay? Manganese has a 3d5 electronic configuration when you take away 2 electron. But if I take away 3 electron, then it will be 3d4. And 3d4 is unstable, guys. 3d4 is unstable. It's not so stable, right? But manganese, when you take away 2 electron, it was very stable. It had half filled. It was like, yay, I'm so happy. I have half filled, right? Yes. But from iron has a 26 atomic number. That means 3d6 4s2. If you take away 3 electron, then what will happen? Then it will have a stable electronic configuration of 3d5, which is why iron has a lower ionization enthalpy, third ionization enthalpy. Yes, absolutely right. Learning for life. Yes, do we understand this, guys? Very good. All righty then. All righty. Okay. Now everybody, I believe that we have to move a little faster because I have taken much longer time for the basics. Now I'm going to go through the faster route, that is here. Common oxidation state, where is atomic radius? Atomic radius. Lanthanoid contraction. Ionization enthalpy is done. Now we come across oxidation state, everybody. Okay? Alright, chalo guys, let us come to oxidation state, everyone. Now, what is, somebody had asked me in the very beginning of the session that, ma'am, what is the common oxidation state? Everybody, what is the general electronic configuration of this 3D series, guys? Everybody, what is it? It is 3D 1 to 10, 4s 1 to 2, isn't it? This 4s electron, these 2 electrons, they can be easily given away, right? Yes, they can be easily given away, right? So that means that the most common oxidation state, see, sparkle filter, no. That is why focus up in the session instead of asking what is your Snapchat ID. Virtual punch and virtual slap, you understand? That is what you're going to get. That is what you're going to get, okay? Yes, right. So here what is happening is, if you give away 2 electrons, then it goes to the +2 oxidation state. And +2 is the most common oxidation state for all the 3D series except scandium. Scandium can only show you +3 oxidation state. Scandium can show you +3 oxidation state and not +2 oxidation state, because scandium has an electronic configuration of 3D14s2. That means these 2 electron and this electron, if it gives away, then it attains the stability of a noble gas, which is +3. Okay, all right. Yes, why does it do so? That is because there are fewer electrons to lose or share. Hence, scandium is an exception of +3 oxidation state. Rest everything has +2 oxidation state. Check it out. Titanium +2, vanadium +2, chromium +2, manganese +2, iron +2, cobalt +2, nickel +2, copper +2, and zinc also +2. All of them, they show you +2 oxidation state, which is why they are +2 is the most common oxidation state. Yes, are we understanding, everybody? Yes, yes. What is your doubt? Can we study from Tattva? Yes, you can study from Tattva. Okay. All right. Now, guys, let us come back to the point that 3D5. Why do we say that the half-filled and the fully filled, electronic configuration of D, why are they so stable? Why are they so stable? So now you have to understand, everybody. Okay, let us try to understand this. Okay, the d orbitals, I can keep it like this, right? Yes, the d orbitals, basically there are 5 boxes that are at the same energy level, right, everyone? Try and understand, everybody. Try and understand this. Yes. Naveen, Mohit, Twinkle Stars, Senthil, Jagadishan, Learning for Life, everyone. Mathan, everybody. Please focus up here. Focus up and tell me. So the d orbitals, they have 5 boxes, right? Those 5 boxes, they have equally same energy. They have equally same energy. Now these 5 boxes, each of them have 1 1 1 1 1 electron. That means all the 1 1 1 electron, they also have same energy. Now, does it matter if this electron goes to the fourth box, or the 5th electron, they come to the 2nd box? What if they exchange their position? Does it matter? It doesn't matter. It doesn't matter, because they have all same energy. Because all of them have the same energy, right? It doesn't matter. Now that, so the exchange energy, yes, when they are, when they are going into different boxes, they release some energy. That energy is called as exchange energy, right? That energy is called as exchange energy. And that exchange energy is the highest in case of D5 or D10. Obviously, if there is D3 electron, that means there can be how many exchanges? 1 can go to 3, 1 can go to 2, 2 can go to 3, 2 can go to 1, 3 can go to 1, 3 can go to 2. So that means each electron has a tendency to change its position twice, right? Altogether, D3, there can be 6 exchange energies, right? There can be 6 exchange energy. But in case of D5 and in case of D10, guys, look at it. 1 can go to 2, 3, 4, 5. 5 can go to 4, 3, 2, 1. Each of them have 4 options. That means there can be 20 exchange energies. And similarly for D10, there can be 20 exchange energies. Right? So that means that there is a huge exchange energy that can be released, and that is also attributed to the D5 and D10 stability. Now do we understand why is it that the D5, the half filled and the fully filled, why are they so stable? Now do we understand, everybody? Why is it so stable? Yes, why is it so stable? Do we understand this, guys? Yes, because there is so much of exchange energy and they can, take away another position. They do not want somebody else to take up their position because they can do it, right? They can do it on their own. Like for example, the Tata group or the Ambani group, right? The Tata group and the Ambani group, they're a very family oriented business. Why? Because in their family itself, there are so many people, right? The Tata group, they have a son, they have a daughter. The son has they have a daughter-in-law, they have a son-in-law. The son-in-law will become some board member. The daughter-in-law will become some manager of the board, right? They can do all of these, isn't it? So what happens? They do not require outside people to handle their positions. Getting my point? Getting my point? In their whole family, they can, exchange their position and they can try and make it better, right? So the stability of the Ambani group and the Tata group, it's a legacy they have created for such a long time. They're all there. But if you look at the startup culture, now, what will happen? What happened to all these other educational institutions? What is happening? Somebody is saying that, oh, this company is failing. Somebody is saying that, oh, this company is failing. Why? You have to bring in more people from the outside who are not really oriented about creating your business. They are not from family. They are not from a family, right? But here, what is happening? Here, the exchange energy, when they change their position, they release energy which is called as exchange energy. And because of this exchange energy, the attribution of the stability of D5 and D10 is much higher. All right? Yes? Of course they can. Of course they can. But tell me, how many exchange energy they can release? For D2, 1 can go to the second position, 2 can go to the first position. That's it. 2 exchange energy. 2 exchange energy, is it equal to 20 exchange energy? No. No. That is why. Okay? That is why. Yes? That is why. Got it, everybody? Mohit, I have already explained, bacha. Mohit, I've already explained, okay? What? I'm talking about caste. What? What? Where do you get the caste from? Dude, don't do that. Don't do that. I'm very careful about what I say in my class. Don't put all these. No. What are you talking about? Rahul, stop. What are you talking about? I spoke about Tata Group and Ambani Group. How did you find this? No, Sparkle, no. There was nothing about caste. What's wrong with you? My goodness. You are going to make me, you are going to get me kicked out of Vedantu. I did not say anything about caste, guys. Oh my God. You're going to kill me. You'll send me to jail if you talk about this. Okay, ma'am, it seems. Wow. Bonkers you guys are. Tata Group and Ambani Group, and then I spoke about education sector. And you tell, no, I cannot chill. This is a non-bailable offense in India. Talking about caste. It's a non-bailable offense. If I go to jail, nobody will be able to bail me. I cannot chill. Sorry. Whew. You just scared me. Absolutely. It's about life and death, guys. What is wrong with you? My heartbeat has, gone up. Seriously, I'll cry now if you say that. What are you guys talking about, guys? I did not say anything like that. What's wrong? Don't do that in the chat box. Very wrong, guys. Very wrong. This is not done. Absolutely not done, guys. What happened? I was giving you an example of exchange energy related to Ambani and Tata Group. And somebody told me that I am talking about caste. If I'm talking about caste in this class, I don't know how many of you know about this, but talking about that is a non-bailable offense. If I go to jail, none of you will be able to save me. I will not even be bailed. So that's what happened in the class. Alright guys, so yes, do we understand about exchange energy and do we understand about the most common oxidation state? We do, right? Gaurav ji, my God, just please go out of the class. Please go out of the class. Overacting and drama. Will you come and save? You will come and save me from the non-bailable offense or what? Somebody tells me this. Weird. And one more time, if somebody does this, I'm going to stop taking the class. Do whatever you want in your board exam. We will see. Okay? One more time. That's your last warning, guys. Okay. Now everybody, let us come to magnetic properties. Now because of these unpaired electrons that are present with these d block elements, right? Because of these unpaired electrons that are present in these d block elements, they also have magnetic properties. Now what do we mean by magnetic properties? There are two different kinds of properties, that is paramagnetic and diamagnetic, right? Diamagnetic means, okay guys, please understand this, paramagnetic means that they are attracted by a magnet. Diamagnetic does not mean that they are repelled by a magnet, okay? Diamagnetism means that, diamagnetism everybody means that they are not at all affected by the magnetic field, right? Like nothing happens to them. They're not repelled, they're not attracted also, okay? They're not repelled, they're not attracted also. They are only there. Nothing is affecting them, right? So paramagnetism occurs, or paramagnetism can be seen in these d block elements when they have unpaired electron, okay? Whenever they have unpaired electron, there is paramagnetism. You will see that they are attracted towards magnetic field. And whenever they have all paired electrons, everything is paired up, that's when they have diamagnetism. That's when they show diamagnetism. All right. Now, here is a trick for you everybody. If you are asked to calculate the magnetic moment unit everybody is Bohr magneton, and the formula to calculate the magnetic moment is right here, which is mu is equal to root over n multiplied with n plus 2. And what is n here? N is the number of unpaired electron. And what is the unit? The unit is Bm, that means Bohr magneton. Am I clear, everybody? Yes, the unit is Bohr magneton, everybody. Cool? Clear, everyone? Is magnetic moment clear to you all? Is magnetic moment clear to you all, everyone? Yes or no, guys? Yes or no? Yes or no? Magnetic moment is clear to you all? Yes? Okay. All right, guys. Now, let us go towards what else is left, everybody? What else is left? Anything else is left, everyone? Ha. Now, we will come back to the fact that properties of D block, right? Properties of D block. Achha. These D block elements, they can also form colored ion. Once again, now coming back, everybody, coming back to the fact that we had exchange energy. Do you remember? Exchange energy, right? Okay. So everybody, tell me that we all know that here, this is your d orbital. Yes, this is called as degenerate d orbital. Yes, what is this called as? This is called as degenerate d orbital. What is degenerate, guys? Degenerate means, everybody, degenerate means, have a look at it, 1, 2, 3, 4, 5, right? Degenerate means all of them are at the same energy level. Yes, degenerate means all of them are at the same energy level. Right. Now what happens is, because of some other atoms trying to connect with this, they split up. Okay, they split up like this. First what happens, they go to a higher energy level like this, 1, 2, 3, 4, 5. Then what happens is, then they split up. Okay, sometimes what happens, they have 1, 2, 3 here, and they have 1 and 2 here. Now let's suppose that you have, one electron right here. If you give this one electron a little bit of energy, if you give this electron some energy, what will it do? It will go up here, isn't it? It will go up here. Now what is this happening? This is a part of the d orbital. This is also a part of the d orbital. So here what is happening? From d orbital to d orbital, there is a d to d transition, right? There is a d to d transition, which is why you get to see some colored ions, and that is something that we will be reading about in the coordination compound chapter also. Yes, that is why we will be reading about the coordination compound also. Here, why do you see colored compounds in the D block elements? That's because there is DD transition. Okay, there is DD transition. Got it, everybody? Clear? All right, moving on now. Apart from this, the D block elements, they also show you catalytic property. Why so? Number one, they have huge surface area, right? They have huge surface area, and in that surface area, many reactions can happen faster. All right. So catalysts, what do? They provide an alternate path. That means they provide a different path for the reaction to happen, and that means that the reaction can happen faster. For example, in Haber's process, when we are making ammonia, finely divided iron particles are used, as well as molybdenum powder is used for this process. And these two, that is iron and molybdenum, they act like a what? They act like a what? Catalyst. Yes, they act like a catalyst. Okay? And similarly, you will see that in Oswald process, platinized asbestos is used as a catalyst. Okay, in contact process, when you are preparing sulfuric acid, you will see that platinized asbestos or vanadium, divanadium pentaoxide is used. Okay, in all these cases, what do you have? In all these cases, we are trying to show that there is catalysis. Okay, there is catalysis. Cool? All right, everybody? Yes. Now we also want to talk about interstitial compounds. So I have just told you that you know that these D block elements, they have huge surface area, and sometimes in the gaps that they have, right, these kind of gaps that they have, here what happens, very small elements like hydrogen, nitrogen, carbon or boron, they get trapped inside this gap. Okay, And when they get trapped inside this crystal lattices, they become an interstitial compound. Now these interstitial compound, they do not lose their electrical conductivity or their heating conductivity. They have almost all the properties of a metal as they should have, and they become very hard, everybody. They become very hard. In fact, if there are boron, if boron is present in an interstitial compound, then do you know what happens? It almost approaches the diamond in hardness, everybody. Yes, so they retain metallic conductivity, but they have higher melting point, and they have higher melting point, plus they are harder than the pure metal, everyone. Okay, all right, everybody. Yes, guys, are we guys understanding? Yes. Okay, all right. Yes, 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 yes. Okay, moving on, everybody, moving on. Formation of complex compounds. The D block elements, they also form lots and lots of complex compounds. Why? Because comparatively they are of smaller size. Yes, they have high charge on ions. You saw, na? M plus 7. Manganese can go up to plus 7 oxidation state. So that is a great charge. Plus 7 oxidation state, you will never find it on sodium, magnesium, beryllium, rubidium, cesium. You can never find it. So that is why. They also have a very high E/M ratio, right? And they have available vacant d orbitals for bond formation, which is why you get to see a lots and lots of coordinate complexes. Okay? They also do form alloy. Why? What is alloy, guys? Alloy is basically a homogeneous mixture of solid solution. Now you saw that these D block elements, didn't we see in the table, everybody, that they have comparatively sizes, right? Their sizes, they don't increase so much. Their sizes are also very similar, right? They also have, ionization enthalpies are comparative in their, comparatively very similar, isn't it? So that means that you can actually mix them together. And because they have all very similar radii, similar properties, the alloys are readily formed for the transition elements. They are often hard. They are often very high melting point. For example, you have steel, you have bronze, you have brass, etc. Somebody is asking me what is E/M ratio. Can somebody tell me what is E/M ratio? Structure of atom bhul gaye, huh? Yes, structure of atom. Yes, guys. What is it that I have left? Tell me. Ionization enthalpy, covered, right? Covered. Oxidation state, I have just covered. That manganese can show you plus 7 oxidation state. What is the most common oxidation state? I have just told you that plus 2 is the most common oxidation state for everything, right? What else? What else do you want to know? What is it that I have not taken? Why? Why do you keep blaming the teacher? You guys know too much. Then study on your own. One class that I have to take, and today evening also I have to take, I really do not know how to handle you guys. Really do not know how to handle you guys. Anyway, now coming back to it, everybody, we all know that manganese can show you oxidation state from plus 2 to plus 7, and the lesser number of oxidation state at the extreme end, it is because they have very few electrons to share, or there are too many of d electron. That means that they have all paired electrons. So that is why they are not really there to lose the electrons. For example, zinc has what? 3d10 4s2. All the electrons are paired. It does not want to give away its electrons, right? So here, everybody, come back. Yes, here, thus early in the series, scandium is virtually unknown, and titanium, see scandium 2, you will never find scandium 2 because scandium can give away the last electron as well, and it will become a stable scandium plus 3 oxidation state. See, virtually unknown. Titanium 4 is very stable, but titanium 3 or titanium 2 is known. Why so? Because titanium, scandium, then titanium. Titanium has an atomic number 22. 22, that means 3d2 and 4s2. It can give away these 2 electrons and it can become titanium plus 2. It can give away another electron from here and it can become titanium plus 3. But losing the last electron, then the ionization enthalpy goes very, very, very high. It goes very, very, very high, and that is why you will not hear about titanium plus 4 so much. It is not so stable. Okay? At the other end, the only oxidation state of zinc is plus 2. Why? Because all the d electrons are paired and the d electrons are not involved in the oxidation state. Okay? Alright, all of these I have told you. All of these I have told you, isn't it? All of these I have told you already, isn't it? Everybody, let me know. Haven't I told you? Huh? Haven't I told you all of these? I have told you. I have told you. Who was that fellow who told me that, ma'am, I think you have skipped a lot? Please tell me. What is it that I have skipped? What is it that I have skipped? Anything that you want to say? Chalo, theek hai. Now, see. The maximum oxidation state of reasonable stability correspond in value to the sum of S and D electrons up to manganese, followed by a rather abrupt decrease in stability of higher oxidation state, so that the typical species to follow are Fe2 and 3, cobalt 2 and 3, nickel 2, copper 1 and 2, and zinc 2. That means what they're saying is that the oxidation state increases up to manganese. After that, you do not see till +7 oxidation state anywhere from iron to copper. You do not get to see it at all. Got it, everyone? Yes, you do not get to see it at all. Now what happens is the variability of oxidation state, a characteristic of transition element, it arises because of incomplete filling of d orbitals in such a way that their oxidation state differ from each other by unity. 1-1, just by 1-1 position, just by 1-1 unity, you can see that there is a change in the oxidation state. Okay, there is a change in the oxidation state. For example, see, vanadium can show you 2, 3, 4 and 5. This is in contrast with the variability of oxidation state of non-transition element, where oxidation state normally differ by a unit of 2. For example, when we were studying about P block, guys, in P block, don't you remember that in P block we saw that carbon family had what? +2 oxidation state, and there was +4 oxidation state, right? Lead was not showing +4 oxidation state because of inert pair effect. It was only showing +2 oxidation state. But here you see that vanadium can show you vanadium +2, vanadium +3, vanadium +4, vanadium +5. That means by 1-1-1-1 thing, it can increase the oxidation state. Okay. Now here there is another interesting feature in the variability of oxidation states of the D block elements, and that is noticed among the group 4 through 10. Although in the P block, the lower oxidation state are favored by the heavier metals due to inert pair effect. That is the example I just gave you about lead. Yes, the opposite is true in the groups of D block. In the D block, you will see the heavier elements, they can show you higher oxidation state. Okay, they can show you higher oxidation state. Now, for example, in group 6, molybdenum can show you 6 oxidation state, tungsten can show you +6 oxidation state, chromium can show you 6 oxidation state. However, chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas molybdenum O3 and tungsten trioxide are not. Okay. All right, everybody. Yes, 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 everybody. Cool. Getting it? Yes. So this is basically the oxidation state that we are talking about. Okay. This is the oxidation state that we are talking about. Okay. Now, the low oxidation state are found when a complex compound has ligands that are capable of pi acceptor character in addition to the sigma bonding. What is this? Metal carbonyl. Metal carbonyl. Do you remember that synergic bonding? The synergic bonding, the back bonding. Do you remember, everybody? We have learnt about it. Yes? Haven't we learnt about it, guys? Absolutely. This we will be learning about it a little more in coordination compounds. Okay? In coordination compounds. Now, everybody, coming back to standard electrode potential, everyone. Coming back to standard electrode potential, see, in the M2+2M standard electron, see, here, understand. Table 8.4 contains thermochemical parameters related to transformation of the solid metal atoms to M2+ ions in solution. That means, see, transformation of solid metal atom to M2+ ions in solution. That means I have a metal atom like this. I have to convert this to M2+ aqueous. I have to convert this to M2+ aqueous. But is it very simple? Is it as easy as just taking one step? No. First of all, I will have to give it sublimation energy to convert it into gaseous phase. After that, I have to give a 2 ionization energy, that is ionization energy 1 and 2. Then I will be able to convert it to M2 plus. From here, I have to give it hydration enthalpy to convert it to M2 plus aqueous. That means that there are 3 or 4 processes that we have to follow to get it to M2 plus aqueous form. So, we are going to see a table, we are going to see this image, and we are going to understand that what is happening. So we see that for titanium it is low, for chromium it increases, for manganese it is again low, for iron it has increased, for cobalt it has again decreased, for nickel it has increased a little bit, but for copper it is the highest. For copper, it is the highest, everybody. Why is it the highest for copper? That's because, again, it's very simple, very easy. I have told you, everybody, that copper, when you take away 2 electrons, only then the hydration enthalpy is compensated by the high ionization enthalpy. When they are compensated well, that is when the copper 2 plus ions are going to be stable, but it is not going to be stable for copper plus ions. That is what is written here. See, the unique behavior of copper having a positive E0 accounts for its inability to liberate hydrogen from acid. Now you must have seen the reactivity series, right? In the reactivity series, hydrogen comes above copper. So that means that if you try and make copper react with hydrogen also, hydrogen gas will not be liberated. Hydrogen gas will not be liberated at all, right? So only oxidizing acids such as nitric and hot concentrated sulfuric acid, they react with copper, and the acids being reduced. Okay, the high energy to transform copper solid to copper 2 plus aqueous is not balanced by its hydration enthalpy. Are you getting it? Are you getting it? Did I say ulta? I think I said ulta, sorry. Yes, copper salts are colorless. Why copper sulfate haven't you seen? What happens to copper sulfate? Isn't it blue color? It is blue color, no? Who said that copper salts are colorless? It's not colorless. They have color. Yes. Yes. So what happens is that copper, when you try to convert copper from solid to copper 2 plus aqueous, what happens is the high energy that it requires to transform, that means that you have to give sublimation energy, then you have to give ionization energy 1, ionization energy 2, and then hydration energy will be released to make it form into copper 2 plus. It is so high that it is not balanced by the hydration enthalpy. So the general trend towards less negative E0 values across the series is related to the general increase in the sum of the first and second ionization enthalpies. Do you get it? In case of copper, however, the sum of the first and the second ionization enthalpies becomes very high. It is interesting to note that the value of E0, that is standard electrode potential, for manganese, nickel and zinc, they are more negative than expected from the trend. Guys, are we understanding? Yes. Anhydrous copper salts can be colorless. Yes. Anhydrous ones are colorless, but copper sulfate dot 5H2O, that is blue in color, if you try to heat it, the blue color will go away. The blue color will go away. All right, everybody, is this clear, guys? Standard electrode potential, do we understand, everyone? Yes. Chalo, moving on. Now, similarly, you can study for the trends in M3 plus to M2 plus standard electrode potential. Now, an examination of the E0 M3 plus M2 plus value shows the varying trends. The low value for scandium reflects the stability of scandium 3 plus C. Check it out. Check it out. You understand here where is 8.2, table 8.2, table 8.2. Where is table 8.2, guys? This is table 8.2. Here, see, for scandium, everybody, the value is very low, so low that they have not even mentioned it. The value is so low that they have not even mentioned it. That means that scandium is very, very stable in its +3 oxidation state. Got it, everybody? Yes, I said it ulta. Yes, bacha, I've said it ulta. Yes. Yes, learning for life, absolutely. That is the correct version. I said it ulta. I said that they're compensated well. No, they're not compensated well. Actually what happened is the ionization enthalpy 1 plus 2 plus sublimation energy is so much higher that the hydration enthalpy is not able to compensate for it. Okay, they have not compensated for it. Okay, just told you, Nababa. Just told you, yaar. Here, what are you doing? Now, the highest value for zinc is because of the removal of an electron from the stable D10 configuration of Zn2 plus. And the comparatively high value for manganese shows that Mn2 plus is particularly stable, whereas comparatively low value for iron shows the extra stability. Again, guys, I have taught you all of these things, okay? I have taught you all of these things already from that table. I told you Fe3 plus, Fe2 plus, Mn2 plus, Mn3 plus, all of these are done, isn't it? Yes, all of these are done. Chalo. Now moving on to stability of higher oxidation state. So we notice everybody, that what happens is that the +7 oxidation state for Mn is not represented in simple halide. That means manganese, when it reacts with the halogen family, fluorine, chlorine, bromine, iodine, that time you do not see the +7 oxidation state. That time you do not see the +7 oxidation state. When does manganese show you +7 oxidation state? Only when it is in relation with oxygen. So everybody, coming back to it, the highest oxidation states that are achieved in case of halides are tetrahalides for titanium, pentahalide for vanadium, and hexahalide for chromium. The +7 oxidation state for manganese is not represented in simple halide, but MnO3F. That means manganese with oxygen and fluorine can show you a higher oxidation state. Yes, everybody? Okay. Now, beyond manganese, no metal has a trihalide except iron X3. That means that till iron and cobalt, you can still see trihalide. After that, you do not get to see trihalide. See, copper, zinc, nickel, they do not show you trihalide. Okay? All right, everybody. Why so? You know the electronic configuration. Once again, the electronic configuration is the reason why this happens. Okay? All right, everybody. Now, the ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as in the case of cobalt F3, or higher bond enthalpy terms for the higher covalent compounds, that is vanadium pentafluoride or chromium hexafluoride. Now, V plus 5 is represented only by VF5. The other halides, however, undergo hydrolysis to give oxohalides, that is VOX3. Another feature of fluoride is their instability in the low oxidation state. Everybody, do we guys understand this? Do we guys understand this, everyone? Yes or no? Yes or no? Okay. Now coming back to this part, everybody. So we saw that manganese does not form +7 oxidation state with simple halide. However, when it is in relation with oxygen and fluorine, it can show you +7 oxidation state. Why so? Because now not only you have a very high electronegative fluorine, but you also have high electronegative oxygen. And you all know that oxygen can also form double bond. Oxygen can also form double bond, everybody, which is why you get to see +7 oxidation state with manganese, oxygen and fluorine, but otherwise in a simple halide you do not get to see it. Do I make myself clear? Do I make myself clear, everybody? Is this clear, guys? Is this clear to you all now? That why this happens? Why you get to see this? Yes, why you get to see this? And here is the reason, everybody. Here is the reason. Although V plus 5 is represented only by VF5, you do not get to see VCl5, VBr5. Why? Because the other halides, they go through hydrolysis and they form oxohalides. Okay? They form oxohalides. Okay? Yes, yes, yes. Double bond. Yes, double bond. Yes, yes, yes. Yes, absolutely, bacha. Absolutely. Yes. Very good. Okay? Alright, so trends of stability in higher oxidation state done. Now guys, coming to, somebody had asked me in the very beginning of the session that ma'am, Cu plus 1. Cu plus 1. Can you talk about Cu plus 1, everyone? So let us take a look at it. And the same applies to, ठीक है. Have a look, see. Another feature of fluorides is their instability in low oxidation state. So the halides, that means fluorides, they are not very stable in a low oxidation state. That means the fluorides, they are usually they maintain stability when they are in +3 oxidation state, when they are in +2 oxidation state, when they are in +3 oxidation state, +4 oxidation state, but they're not very stable in +1 and +2 oxidation state, right? Similarly, you get to see this with copper halides, okay? So we know that on the other hand, all copper 2 halides, that means Cu in +2 oxidation state with halides are known, but copper iodide is not known. Why? Because Cu2 plus oxidizes iodine to I2. Yes, what does Cu2 plus do? See, if you take Cu2 plus and if you mix it with 4I minus, it will form Cu2I2 plus I2. What will it form? It will form Cu2I2 plus I2. But many copper 1 compounds, they are unstable in aqueous solution and they undergo disproportionation reaction. Guys, do you understand what was disproportionation reaction and redox reaction? That the element has to be in an intermediate oxidation state. Now copper 1 is an intermediate oxidation state, isn't it? Because copper can go to a lower oxidation state which is 0 and it can go to a higher oxidation state which is 2. So here what is happening is, when you take copper in +1 oxidation state, it disproportionates. It goes to 0 oxidation state, that means in its elemental form, and it goes to a higher oxidation state, that means it gets reduced as well as oxidized, and that is why copper in +1 oxidation state is unstable. Do we understand, guys? Do we understand this, guys? Yes or no? Tell me. Yes or no, guys? Do we understand this? Yes? Very good. Chalo. Now, the stability of copper 2 plus rather than copper plus is because of the much more negative hydration of Cu2 plus than copper plus. Remember, what did we tell you? The ionization enthalpy is 2. Sublimation enthalpy is not compensated by high hydration enthalpy. The hydration enthalpy is also very high. The hydration enthalpy is also much more negative, but that is the reason why copper 2 plus is more stable than copper plus, which more than compensate for the second ionization enthalpy. Now, do you understand, everybody? So basically what we are trying to say is, try and understand this, that copper, when it has to get converted to Cu2 plus, what are the things that we require? We require here sublimation energy, we require ionization enthalpies 2, plus we require hydration enthalpy. Now what has been observed is that the sublimation plus IE1 plus 2 is higher than the hydration enthalpy, no doubt about it. But somehow the ionization enthalpy that you have here, that and the hydration enthalpy, they are similar in nature, which is why the stability of copper 2 plus is more. Getting it? Getting it? Yes, Govi, what is your doubt? Do you guys understand? Now read this sentence once. Read this sentence once, everybody. Just read this sentence once and just ponder on what I have told you. Just ponder what I have told you, everybody, and read this sentence once. है ना? We have understood everything. Okay. All right, bacha. Chalo, theek hai. Okay, moving on. Now, the ability of oxygen to, okay, see. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides, and the highest oxidation number in the oxide coincides with the group number, and it is attained in scandium 2O3 to Mn2O7. Now, manganese belongs to group 7. and it has +7 oxidation state. Scandium belongs to group 3. It has +3 oxidation state. So what we are trying to say is that the whatever is the oxidation state that corresponds to the group number, okay, it corresponds to the group number. Yes, Aditya, Rajesh, yes, that is the answer. That is the answer. Okay, that is the answer. Yes. However, after group 7, you will not see any high oxidation state. You will not see higher oxides of iron above Fe2O3. Although you have ferrates, that is FeO4 2-, and they are formed in alkaline media, but they readily decompose to Fe2O3 and O2. Besides the oxides, there are oxocations that stabilize vanadium 5 as VO2 plus, V4 as VO2 plus, and Ti4 as TiO2 plus. Okay. So the ability of oxygen to stabilize this high oxidation state exceeds that of fluorine, and thus the highest Mn fluoride is MnF4, whereas the highest oxide is Mn2O7. Why? Why does oxygen show such higher oxidation state? Because the ability of oxygen to form multiple bonds to metal explains its superiority. In the covalent oxide Mn2O7, each manganese is tetrahedrally surrounded by oxygens, including an MnO-Mn bridge. The tetrahedral MO4N- ion are known for vanadium, chromium, manganese 5, manganese 6 and manganese 7, everybody. Okay? Alright? Yes, Ray. Yes. No. Cu+2 is more stable. Cu+2 is more stable. Okay? Alright? Yes. Do we understand this, guys? And this is the table to show you what are the oxidation state. Okay? Yes, everybody. Do we understand this? Are we good to go? Are we good to move ahead, everybody? Are we good to move ahead, everyone? Yes? Lakshita, Sparkle Filter, Kavi. Yeah? Are we all good to go? Okay, Lakshita, you can leave the class. Go ahead. Sleep. No worries. Then come back and tell me how your marks are also boring, okay? Go ahead. You can leave the class. No problem. 100%, 110% understood. Thank you. Okay. Guys, now moving on, chemical reactivity and values of E0. Okay? Chemical reactivity. Let us quickly go to chemical reactivity. Magnetic properties I've taught you already. Yes. So the transition metals, they vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in many mineral acids. What are mineral acids? Hydrochloric acid. Yes, what are mineral acids? Sulfuric acid. What are mineral acids? Nitric acid. These are all mineral acids. Okay? Although a few are noble, that is, they are unaffected by single acids. Now the metal of the first series, with the exception of copper, they are relatively more reactive and they are oxidized by 1 molar H plus. Yes, that means that if you take 1 mole of H plus ions, they are going to get oxidized. Okay? Although the actual rate at which these metals react with the oxidizing agent like hydrogen ion is sometimes very slow. For example, titanium and vanadium in practice are passive to dilute non-oxidizing acids at room temperature. That means that titanium and vanadium, they do not react with dilute non-oxidizing acids at room temperature. Now the E0 values for M2 plus M, which we have seen in that table. Do you remember? In that table. Yes, in that table we saw. Very good. Yes. Indicate a decreasing tendency to form divalent cations across the series. This general trend towards less negative E0 values is related to the increase in the sum of the first and the second ionization enthalpies, and it is interesting to note that the E0 values for manganese, nickel and zinc are more negative than expected from the general trend, whereas the stabilities of half-filled D subshell in Mn2 plus and completely filled D subshell in zinc are related to their E0 values. For nickel, E0 value is related to highest negative enthalpy of hydration. So here they are explaining. That why in table 8.2, the properties that we saw, why they are like that. Okay, why they are like that. Now, an examination of the E0 values for the redox couple M3 plus M2 plus shows that Mn3 plus and CO3 plus ions are the strongest oxidizing agent. Why? Why so? Because Mn plus 3 will try to get converted to Mn2 plus very easily, isn't it? Yes. It will try to get to Mn+2 very easily in aqueous solution. And because it is going to get reduced, it is going to be a strong oxidizing agent, right? Yes, so the ions titanium 2+, vanadium 2+, and chromium 2+, they are strong reducing agent. Why? Because chromium +2 will try to get to chromium +3. Yes, because chromium +2 will try to get to chromium +3. See, it will try to get to chromium +3. That is why it is going to be a strong reducing agent. Guys, are we making sense, everybody? Are we understanding, everyone? Are we understanding? Yes? Okay. Magnetic property, we have already done, right? Yes. Magnetic property we are already done. Magnetic property is already done. Correct. Very good. Okay. Formation of colored ions already done. Formation of complex already done. Catalytic property already done. Interstitial compounds done. Alloy formation done, everybody. And now finally the last bit of the session, that is potassium permanganate and potassium dichromate. After that we are going to go for coordination compounds. So guys, ready study for the last bit of the session? Are we ready for the last bit of the session? Yes? Yes, SNQs, you must do that. You must do that, okay? You must do that. Absolutely, you must do that. Chalo, before we go to potassium permanganate and dichromate, let us quickly go through some questions, everybody. Let us quickly go through some PYQs. Shall we go through some PYQs, everybody? Arey, F block mein there is nothing, only lanthanoid contraction is there. Nothing else is there in F block. Chalo guys, let us try and solve some questions. So first question is, what are the transition elements? Write two characteristics of transition elements. Prabhu Bacha, like I just told you, yes, F block elements are very easy. Don't worry about it. It just has lanthanoid contraction and nothing else. Yes, nothing else is there. So tell me, everybody, what is the answer here? What is the answer here? What are the transition elements? Write two characteristics of the transition elements. Let us write it down. This may come for 2 marks. Okay. So what are we going to write? We are going to write, everybody, that elements. Okay. Everybody, you can answer, guys. Elements which have incompletely filled d orbitals, yes, in their ground state or in any one of their oxidation state are transition elements. Okay, now let us talk about the characteristics. What are the characteristics, everybody? What are the characteristics, guys? First one is that, you know, they show variable oxidation state, right? They show variable oxidation state. Can we write this down? We can write this down, right? They show variable oxidation state. Number 2, what can they do? They can show catalytic properties. They show catalytic properties. Can we write this? They show catalytic properties. Absolutely, we can write this as well. Correct? Yes, so this question is over. Next question. Account for the following. Zinc is not considered as a transition element. Why so? Because in electronic configuration of zinc, we have completely filled d orbital. Completely filled d orbital in the ground state, as well as in their common oxidation state. That is why they are not regarded as transition elements. See, this question is also done. See, now you have to know the electronic configuration, guys. That is why I kept telling you that at least for the first 3D series, you must know the electronic configuration. See, it is very important, isn't it? Now for chromium +3, how can we write? First of all, we will write the noble gas, that is argon. Yes. After that, chromium has what? What is chromium's electronic configuration? chromium as 3d5 4s1, right? So if you take away 3 electron, 4s1 gone, and 2 electrons from 3d5 gone, so it will be 3d3. Got it? Yes. Now if we go to B, that is copper plus. Copper has what? 3d10 4s1. So that means we can write it as AR 3d10. Am I right? Absolutely. Let's come to C here, everyone. For C, you can write it as CO plus 2, right? Cobalt is plus 2. Cobalt will have argon right here once again, and cobalt has what? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt. Cobalt is 27. 27 means 3d7 4s2. So if 2 electrons goes away, then it will be 3d7, right? Makes sense? Okay. Option D is manganese, guys. Mn plus 2. Mn plus 2 will have what? Again, here you write argon and you write 3d5. Make sense? Very good. Next, guys. Assign a reason for each of the following observation. The transition metals, with the exception of zinc, cadmium, and mercury, are hard and they have high melting and boiling point. Secondly, the ionization enthalpies first and second in the first series of the transition elements are found to vary irregularly. Who can answer this? Who can answer this, guys? Who can answer this, everybody? Yeah? Who can answer this? Come on, guys, answer. No one is going to answer. Unpaired electrons and empty d subshell due to metallic bonding. I am hearing many different kind of answers, guys. How do I expect all of it? How do I accept all of it? I have to accept only the correct answer. So what is your answer? What is your answer, guys? Unpaired electrons, huh? Most of the students are saying unpaired electron. Is it unpaired electron, guys? Is it? Chalo, let us answer, guys. Let us answer. So, we know that, see, for the first one, as we move along the transition metal series from left to right, from scandium to zinc, what happens? The atomic radii, it decreases, isn't it? Yes. The transition metals, they have hard and they have high melting and boiling points. So, we know that the atomic radii decreases. And why does it decrease? It decreases because of nuclear charge. Effective nuclear charge is increasing. Very good. Now the atomic volume decreases. At the same time, the atomic mass increases, right? At the same time, the atomic mass is increasing. Apart from that, we also know that in the transition metal, when you go from left to right, they are hard and have the high melting point. Why so? Because of the unpaired electron. The enthalpy of atomization is also higher. Absolutely. What is it? Enthalpy of atomization is higher. Enthalpy of atomization is higher, right? Unpaired electrons are higher, isn't it? That is why that happens. Okay? Secondly, the ionization enthalpy, the first and the second in the first series of the transition elements are found to vary irregularly. Why so? Why is there irregular variation of ionization enthalpy? That is because the 3D configurations are also different. Now, the 3D configurations are different. And in the 3D configuration, we know that D5, D10 and D0, they have exceptional high stability. High stability. So that means because of the weird variation of the 3D configuration, we see that the ionization enthalpies are also different. Henna? Understood, everybody? Will you all be able to write this? Yes, Kavi. Thank you so much. Thank you so much. That's absolutely the correct answer. Very good. Chalo. Next question, guys, is assign a reason for the following. Copper 1 ion is not known to exist in aqueous solution. Why so? Why so? I think we have done this, guys. We have done this, right? Copper 1 is not known. Why? Don't we know this? Why are they unstable? Because of disproportionation reaction. disproportionation reaction. What happens? 2Cu plus, if you take, it will become Cu2 plus and Cu. That is why it is not stable. Yes. Second, both oxygen and fluorine stabilize high oxidation states of transition metal, but the ability of oxygen to do so exceeds. Why is oxygen superior? Because of tendency of oxygen to form multiple bonds, isn't it? Tendency of oxygen to form multiple bonds. Am I right? Very good. Next question, guys. Yes, next question is, the enthalpies of atomization of transition elements are high. Why? Why is it high? Large number of unpaired electron. Large number of unpaired electron. Yes, right, everybody. That is why they have stronger bond, and that is why enthalpy of atomization is very high. You guys are going to write a sentence. Okay, I'm writing only one sentence, but you guys have to write. Now, the transition metals and many of the compounds, they act as a good catalyst. Why? Why can they do this? Because they can exhibit multiple oxidation state. Why are they used as catalysts? Because they can exhibit multiple oxidation state, plus they have larger surface area. And third one, the E0 value. See, I told you guys, Mn3 plus to Mn2 plus couple is much more positive than chromium 3 plus to chromium 2 plus. We all know that much larger third ionization energy of Mn, where the required changes from D5 to D4, right? Mn, when it is trying to go from 3 plus to Mn2 plus, what is happening here? What is happening here? What is happening here, everybody? You are trying to convert D4 to D5. So obviously it is going to be much higher, right? Obviously it is going to be much higher. So this is the responsible reason here. Yes. And this also explains that the +3 oxidation state, this +3 oxidation state of manganese, it is of little importance. It is hardly even there. We don't even have to talk about it, because manganese never wants to go to its +3 oxidation state. Manganese does not want to go through its +3 oxidation state. Okay? All right, everybody. Yes, guys. The next question, shall we do it now? Or now shall we go back and study potassium permanganate and chromium, everybody? Potassium chromate and potassium permanganate, shall we study that? Shall we study that, everybody? Yes? Guys? Yes, Krisha. There are a lot of reasons and you can study. Chalo. Now let us quickly go back to our potassium chromium and potassium permanganate. Here we are. Yes. Okay. So we come across potassium dichromate. Okay. We are going to study about potassium dichromate, everybody. Are you all with me? Quickly go and call up your friends, everybody, how to find whether the metal is showing DD transition or not. I'll tell you. Don't worry, I'll tell you. Prashi, we have just done so many questions, yeah, bacha. We have just done so many questions. No, we will come back to the question. Don't worry. You need some break after this. After this chapter, I'll give you a break, okay? After this chapter. Yeah, we will complete. No, you leave it all that to me. We will complete, don't worry. After D and F block, coordination compound is going to be very easy. PYQs, I'll show you where to get PYQs. Chalo. So guys, we're going to go for potassium dichromate, that is K2Cr2O7. So potassium dichromate is a very important chemical that is used in, everybody mark it up, that is used in leather industry, and it is used as an oxidant for preparation of many azo compounds. Remember, in your amines chapter, you have diazo compounds, diazonium salts, azo dyes. Exactly. In many azo compounds it is used. Now dichromates are generally prepared from chromate. How do you prepare dichromate? You prepare dichromate from chromate, okay? Which in turn are obtained by the fusion of chromite ore. So, everybody, how do you make dichromate? You make dichromate from chromate, okay? From chromate, you make dichromate. Cool? How do you make chromate? You make chromate from chromite. Are you getting it, everybody? Are you getting it? Yes. What is happening here? What is happening here? From chromite you are forming chromate. From chromate you are getting dichromate. Okay. Azo compounds in organic chemistry you read, no? In organic chemistry, don't you read about azo compounds? That's what. Yes. So with sodium or potassium carbonate in free access of air, the reaction with sodium carbonate occurs as follows. The first thing that you're going to do is you take FeCr2O4 and make it react with sodium carbonate with oxygen. What do you get then? You get sodium chromate plus iron oxide plus carbon dioxide. Now the yellow solution of sodium chromate, it will be filtered and acidified with sulfuric acid, and from there you will get an orange sodium dichromate. Yes, see, Na2Cr2O7 dot 2H2O, it can be crystallized. Yes, so what do you have to remember? You have to remember this and you have to remember this. Here you are taking sodium chromate, hydrogen, and then you are getting sodium dichromate. After you get sodium dichromate, tell me, do you want sodium dichromate? You want potassium dichromate. So you have to add some potassium chloride. Once you add that, you get potassium dichromate plus sodium chloride. Yes, everybody. And the orange crystals of potassium dichromate, they crystallize out. The chromates and dichromates, they are interconvertible in aqueous solution. Depending upon pH of the solution, the oxidation state of chromium in chromate and dichromate is the same. Now guys, everybody, this part, please everyone read it. Read it, guys. Read it. Quickly read it. I will repeat, but read this. Everybody, read this. I have to go and give my cats a little bit of food. Otherwise, they are shouting from outside. Okay? Everybody, quickly follow this. So yes, guys, as I was telling you, everybody, once again, what did I tell you? First thing first, everyone, take a look at it. You take chromite. From chromite, you get chromate. From chromate, you get dichromate. The first thing that we are going to take is, we are going to take here, see, we are going to take sodium carbonate and we are going to take chromite ore. What are we taking? We are taking chromite ore. Chromite ore, everybody, is 4FeCr2O4. This, when it reacts with sodium carbonate, what do you expect to happen? Obviously, you will get Na2Cr2O4. It is going to form sodium dichromate. Yes. Plus, obviously, you are going to get some carbon dioxide, isn't it? And of course, because you have iron here, you will also get certain amount of iron oxide. Make sense? Make sense? See, I'm telling you, teaching you right away. I'm teaching you. How to remember this equation? Chalo, okay, how to remember this equation? Let us write that down. Here. See, first of all, what are you doing? You are preparing Na2CrO4. Yes. Then from Na2CrO4, you are going to create Na2Cr2O7. Yes. Then from Na2Cr2O7, you are going to prepare potassium dichromate. Isn't it? Yes. Isn't it, everybody? So what did I tell you? You will forget in the exam hall. It is very important, guys. It is this reaction, yes, you have to memorize it. You have to memorize it. 1 second. Let me take a, do I have a blank page somewhere? I don't have a blank page anywhere. Wait. Found it. I'll show you right away. I'll teach you. Don't worry. Okay. See. The first sentence that we read here, what did we read? The first sentence was that, first of all, we take chromite. The chromite is then converted to chromate. The chromate is then converted to dichromate. Yes, we need potassium dichromate. So first of all, what are we taking? We are taking 4FeCr2O4. This is our chromite ore, isn't it? This is our chromite ore. See, this is your chromite ore, correct? Yes. This chromite ore, what are you going to do? You are going to make it react with sodium carbonate. Okay? And you are going to add some oxygen as well. When you do this, what will you get, guys? What will you get? From here, crystal clearly you can see that you will be getting Na2Cr2O4 plus you will be getting Fe2O3 plus you will be getting some amount of carbon dioxide. Am I clear? Am I clear? Is this clear, guys? Is this clear, everybody? Yes? Yes, very good. Okay. Now what will happen? You just have to balance it. Balancing an equation, you know. Balancing an equation, do you all know? Yes? Balancing an equation, do you guys know how to do balancing? Balancing an equation, can you all do this, guys? Nobody is going to tell me. Did I write it wrong? Acha, haan. Na2CrO4. It will form Na2CrO4. Okay? Now this Na2CrO4, right? This Na2CrO4, this particular product. You don't know balancing. Who said you? Who said? मार खाओगे तुम लोग, मार खाओगे, बहुत मार खाओगे तुम लोग. Balancing they do not know, it seems. बहुत मार खाओगे सच्चे में. Now you take this Na2CrO4, okay, and you add H plus. Now you are going to, so this was chromate. From this chromate, now you are going to get Na2Cr2O4, okay, all right. Now this Na2Cr2O4 if you take and you do not need sodium chromate. You do not want sodium dichromate. You want potassium dichromate. So you have to add here potassium chloride. Once you do this, you will be getting K2Cr2O4. And this, my dear student, is just Cr2O4. But do you want Cr2O4? No. Now if you try and balance it, here you will find that, see, you are also adding H plus, right? You are also adding H plus. So this is where you are going to get not CrO4, CrO7. And when you take this CrO7 here plus KCl, you will be getting here potassium dichromate. These are the 3 steps to this reaction. That's it. First of all, you are taking chromite ore. This is your chromite ore. React it with sodium carbonate and oxygen. Then you will be getting chromate. Take the chromate, Add hydrogen, you will be getting dichromate. Take the sodium dicarbonate, add potassium, you will be getting potassium dichromate. That's how you remember it. That's how you remember it. That's it. Yes? Do we understand this? Clear hai? Yes, clear hai everybody? Great. Now, here you have to understand a little bit about the structure, guys. See, this is how your chromate ion looks like, and this is how your dichromate ion look like. And I have already underlined it here that the orange crystals of potassium dichromate, they crystallize out, and the chromate and the dichromates, they are interconvertible in aqueous solution depending upon pH of the solution. The oxidation state of chromium in chromate and dichromate is the same, everybody. Yes, it is same, everyone. Okay? Alright, now the structures of the chromate ion CrO4 2- and the dichromate ion Cr2O7 2- is shown here. Right here you can see the structures, everybody. That's there in your NCERT. Go and take a look at it. Yes. Now the chromate ion is tetrahedral, where the dichromate ion consists of two tetrahedra sharing one corner with CrO-Cr bond angle of 126 degree. Please read these lines a little more, because from here they can ask you reasoning questions. Okay? Then the sodium and potassium dichromates, they are very strong oxidizing agents. The sodium salt has a greater solubility in water, and it is extensively used as an oxidizing agent in organic chemistry. Potassium dichromate is used as a primary standard in volumetric analysis. In acidic solution, it is oxidizing action can be represented as follows. In acidic media, it has an oxidizing action. Read this line, guys. In acidic solution, it is oxidizing in nature. Alright, acidic solution, it is oxidizing in nature. Sanya, doesn't matter. You can take any other potassium salt, bacha. You can take any other potassium salt. However, KCl is the best. KCl is the best. Okay. You can take any other potassium salt, but KCl is the best. That is why we take it. Okay. Alright. Sorry, guys. Now let's have a look at it, everybody. See, oxidizing, right? This is going to oxidize. So everybody, tell me, everyone, 6I minus to I2. I minus is in -1 oxidation state, and when it is going to I2, it is going to 0 oxidation state. What is happening? Oxidation is happening, right? Oxidation is happening. Yes, oxidation is happening. Yes, yes or no? Because KCl dissociates very fast. KCl can dissociate very fast, and that is why we use KCl. Okay? You can take any other salt. No worries about it. You can take any other salt. Okay? Because if you take KCl, then NaCl also forms very easily, right? NaCl can also form very easily, because Na plus and Cl minus, they have a very strong affinity. That is why if you take K2SO4, it will form Na2SO4, no doubt about it. But NaCl affinity is stronger. That is why you take KCl. It is easily formed. Okay? Yes, everybody. See, from H to S. Now find out what is the oxidation state of sulfur. What is the oxidation state of sulfur, everybody? What is it going to be for sulfur, everyone? Quick. What is the oxidation state of sulfur? After that, what is happening here? 3s. See, it is going to 3s. Here also oxidation is happening. Similarly, Sn2 plus to Sn4 plus, oxidation is happening, right? Because oxidation number is increasing. You can see that. Fe2 plus goes to Fe3 plus. So whenever in acidic medium, if you take potassium dichromate, close your eyes and you must know that this will go for oxidation. This will go for oxidation. This is a crystal clear answer. No other doubt. Acidified potassium dichromate, wherever you take, it is going to oxidize. Okay? Very good. Very good. Okay? Alright, guys. Similarly, now See the full ionic equation, you can write it like this. This is the ionic equation that if you want to take a look, you can take a look at this. Okay. Now let us quickly go to potassium permanganate, everybody. Very simple, very easy, exactly same as potassium dichromate, not very difficult. Look at it. Potassium permanganate is prepared by the fusion of MnO2, that is manganese dioxide, with an alkali metal hydroxide and an oxidizing agent like potassium nitrite. This will produce a dark K2MnO4, which then disproportionates in neutral or acidic solution to give you permanganate. So what you do, you take manganese dioxide and then you take an alkali, strong alkali plus oxygen, you will get 2K2MnO4 plus 2H2O. Then you take this MnO4 2 minus, add hydrogen here, that means acidify it, you will get MnO4 minus plus MnO2 plus 2H2O. That means that this was only a preparation. Now we are going to also take a look at, everybody, now we are also going to take a look at the commercial preparation, everybody. And the commercial preparation is where you take manganese dioxide once again, but manganese dioxide is fused with potassium hydroxide and it is oxidized with potassium nitrate. Then you will get manganate ion. Take the manganate ion. This time you are going to go for electrolytic oxidation in alkaline solution and you will get MnO4 minus. Yes? Yes, guys? Yes or no, guys? Do we understand this or not? Okay. Now from here, in the laboratory, how can we prepare it? See, a manganese iron salt is oxidized by peroxodisulfate to permanganate. Peroxodisulfate is this, guys. Peroxodisulfate. Disulfate, that means there are two sulfur and there is a peroxo linkage. So S2O8. S2O8, that means it can be also written as H2S2O8. And can somebody tell me in the chat box what is the name of H2S2O8? Can somebody tell me what is the name of H2S2O8? What is this called as? Marshall's acid or Caro's acid? I'm going to give you the options also. Can somebody tell me what is this name of the acid? Somebody, tell me the answer, guys. H2, S2 and O8. What is the name? No one is telling me, huh? This is also called as peroxodisulfuric acid. Yes, it is an oxo acid of sulfur, guys. Okay, it is an oxo acid of sulfur. And yes, this peroxodisulfuric acid, this is called as Marshall's acid. What is it called as? Marshall's acid. No, bacha, not Caro's acid. This is Marshall's acid. Okay? Alright, yes. Now potassium permanganate, it forms a dark purple, almost black crystal which are isostructural with those of KCl4. That means KClO4 and the potassium permanganate, they are of same structure. Okay, they are of same structure. Okay? Yes. The salt is not very soluble in water, but when heated, it decomposes at 513 Kelvin. Okay? It has two physical properties of considerable interest. Its intense color and its diamagnetism along with temperature dependent weak paramagnetism. Okay? This can be explained by the use of molecular orbital theory, which is beyond the present scope. Right now in D and F block, we are not talking about molecular orbital theory. That is why they are writing that it is beyond present scope. From this chapter, they are not going to ask you molecular orbital theory question. Now, the manganate and the permanganate ions are tetrahedral. Both of them are tetrahedral. As you can see, the pi bonding takes place by overlap of p orbitals of oxygen with d orbitals of manganese. The green manganate ion is paramagnetic. This is paramagnetic. This is paramagnetic. Everybody, please, please. This question they ask you a lot of time, okay? They do ask you this question a lot of time, that out of permanganate and manganate, which one is paramagnetic, which one is diamagnetic. Make a note of it. Make a note of it. Okay? All right. But the permanganate is diamagnetic due to the absence of unpaired electron. Okay? Acha guys, calculate permanganate mein what is the oxidation state of manganese? What is the oxidation state of manganese? 1, 2, 3, 4, 5, 6, 7. 7, right? Manganese is in +7 oxidation state. If it is in +7 oxidation state, is there any d orbital? Is there any electron in the d orbital? None. If there is no electron in the d orbital, can it show paramagnetism? No. So that's it. That's the answer. Easy peasy, biryani, tasty. Yes. Yes, easy peasy, biryani, tasty. Sentil, not today. Okay, not today. No. No. Redox reaction, balancing a chemical equation is your class 11th, bacha. Don't do this. Please don't do this. I really expect and assume that you know all of these things and then you are coming to class 12. This is your board exam. I cannot go to the level of explaining you how to balance ionic, oxidation equation. I cannot. Sorry. Very good. Now, Tiru Selvan has asked us a very, very nice and important question, that if permanganate does not have unpaired electron, then how is it colored? So, in this case, you do not see DD transition, but you get to see the color because of charge transfer. Now, oxygen has a charge. Oxygen has -2 negative charge, and that charge is transferred to the manganese, which is why you get to see color in permanganate. Are you guys getting it? Are you guys getting it, everybody? Yes, this is the answer. Okay? This is the answer. Now, no, Ritis, I just told you not because of DD transition. Ayyo, Allah. If you write DD transition for potassium permanganate, you will get a very big laddu. 0 laddu that you can go to Tirupati and give it to the god. Okay? Don't write due to DD transition. This is not because of DD transition. This is because of charge transfer spectra. Okay? It is in +7 oxidation state. In +7 oxidation state, it has 0 electrons in the d orbital. If it has 0 electrons in d orbital, how is DD transition going to happen? It's not going to happen. Oxygen has charge. From the ligand charge goes to the metal atom, and that's how you see color. Okay? That's how you see color. Cool. Now guys, acidified permanganate solution oxidizes, oxalates to carbon dioxide, iron to iron 3, nitrites to nitrates, and iodides to free iodine. See, once again, same reaction, everybody. Same reaction. You take iron, iron will go get oxidized and it will go to Fe3+. If you take NO2 minus, it will become NO3 minus. If you take I minus, it will become I2. And you just have to balance the electron. You just have to balance the electron, guys. That's it you have to do. Now the full reaction can be written by adding the half reaction for KMNO4 to the half reaction of the reducing agent, balancing wherever necessary. If we represent the reduction of permanganate to manganate, manganese dioxide to manganese 2 salt by half reaction, this is how you can write it. And then we can very well see that the hydrogen ion concentration of the solution plays an important part in influencing the reaction. Although many reaction can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. Permanganate at H plus is equal to 1 should oxidize water, but in practice the reaction is extremely slow unless there is manganese ions are present or the temperature is raised. Okay guys, do we understand this? Great. Now, a few important oxidizing reaction of KMNO4, guys. These are very, very, very important reaction. Each of this, I need you all to go through this. Okay, these reactions are very, very, very important. Absolutely important, guys. Now, how to remember it? Can I tell you, everyone? Can I tell you how to remember it? Shall I quickly give you a hint how to remember this? See, first thing that you are going to write is, okay, first things first, everybody. Have a look at it. So it is K2MnO4, right? How can I write this? Sorry. How can I write this K2MnO4? I can also write it as MnO4 2 minus. If I take away this K2, if I break this, then it will be K plus MnO4 minus, right? Right? So I'm writing it like this, MnO4 2 minus. Okay. Now what will I do? I will take iodine ion. Okay. Let's say that I am taking 10 iodine minus. What will it become? It is going to definitely become, see how I will balance it. See, 10 I minus. I have taken 10 iodine minus ions, right? If that is the case, then what will happen? 10. How do I balance 10? 5I2. It has gone to its elemental state. It has gone to its elemental state. Now what do you have to do? Just balance. See, if you are taking 5I2 this side, if you are getting 5I2 here, that means, and if you have 10I minus here, now what have you done, guys? What have you done? You're trying to balance it, right? This side, if you have taken MnO4 2 minus, do you all agree with me that it will also become Mn2 plus? This will break apart also. This will become Mn2 plus. Yes, this will become Mn2 plus. Now, obviously, I have to balance it. We will balance it later. See, Mn2 plus it will form. Now, you also know from the redox reaction that wherever there is oxygen, on the opposite side, you are going to add water. Do you remember? There are 4 oxygen. There are 4 oxygen here. So why not, let's say I write here, chalo, one second. Let me try and balance it to you for you and show. I can write here 4H2O, right? But if I write here 4H2O, so I have 4 oxygen, but Mn is 2 plus. This does not make sense. I have to write here 2Mn4. That means that this will become 2Mn2 plus. That means that 2 4s are 8. So 4 does not make sense. So here I have to write 8H2O. If I have written here 8H2O and here I have 4 oxygen, that means that 8 plus 2 is 16. 16 hydrogen somewhere I have to add. See, balanced. Did you see? Did you see how I balanced? Did we see how you balanced? Very similarly, let's again do it for iron. Okay, let's do it for iron. See, check it out. For iron, once again, guys, what are we taking? We are going to take MnO4 minus, MnO4 2 minus. Okay, MnO4 2 minus. If we take MnO4 2 minus, we are also going to take Fe2 plus. Yes. What will we get, everybody? We are going to get Mn2 plus. Obviously, Mn2 plus. After that, what are we going to get? We are also going to get Fe plus 3. Right? And here, this side you have oxygen. So, on the opposite side, we will need, let's say, 4H2O. If I have 4H2O, this makes sense here. This makes sense here, everybody. 4H2O. So, 4 2s are 8. That means here it will come 8 H plus ions. Balanced. 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 Balanced here. You can just write here 5 Fe2 plus to 5 Fe3 plus. That's it. See. So do you understand? Are you guys getting it? Acha Senthil, you wanted to ask about this oxidizing reaction. This I'm teaching you, no? This I'm teaching you. Does this make sense, everybody? Will you be able to solve the other equations very similarly? Will you be able to? Can I skip this part then? Can I skip this part then, everybody? Okay, guys. Now we will quickly finish the F block elements. See, the inner transition elements, that is F block elements. The F block consists of 2 series lanthanoids where there are 14 elements and the actinoids where there are 14 elements. The lanthanum closely resemble the lanthanoids, and it is because of this usually included in any discussion of the lanthanoids for which the general symbol Ln is used often. Similarly, a discussion of the actinoids includes actinum. Besides the 14 elements constituting the series, the lanthanoids resemble one another more closely than do the other members of ordinary transition elements in any series. They have only one stable oxidation state, and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along with the series of other similar elements. The chemistry of the actinoids is, on the other hand, much more complicated. The complication arises partly owing to the occurrence of wide range of oxidation state in this element, and partly because of their radioactivity create special problems in the study. The two series will be considered separately here. Thiosulfate. Same na bacha. Thiosulfate is also same. See, you are taking S2O3 minus. You are taking S2O3 minus, but this time now you have taken faintly alkaline solution. If you take alkaline solution instead of water, you're going to add OH minus. S2O3 2 minus will become SO4 2 minus. That's it. Yes, Prabhu, you must. You must. You must. Okay? You must. Yes. Now, guys. Now, everybody. Yes. Come back, everybody. So the electronic configuration of the lanthanum or of the lanthanoids is right here, everyone. And you have 14 elements, that is lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. Now, what are the electronic configuration that you have to know? The electronic configuration that you must look at is, everybody, cerium, okay, gadolinium, okay, terbium, all right, samarium, europium, lutetium. These are the electronic configuration that you must have a look at and that you must know, everybody. Yes, you must know. Okay? No other way to go about it. These electronic configuration you have to know. Okay? What is the most common oxidation state of lanthanum? The most common oxidation state here is +3. Okay? They can show you +3 oxidation state. Okay? All right. Now let us quickly move ahead, everybody. We cannot spend too much time here. All these are done. Acha, here is a cheat sheet of all the KMNO4 reactions also, by the way. Here we have all the cheat sheets. So if you want to go and check it out, the cheat sheet is right here. You can all go check it out. Okay? Everybody, all of you can go through this. Okay? All right, guys. Apart from this, let us quickly read through the sentences. Here we are. So as I was telling you, the oxidation state. In lanthanoids, La2 and Ln3 compounds are predominant species. However, occasionally +2 and +4 ions in solution or in solid compounds are also obtained. This irregularity as in ionization enthalpies arises mainly from the extra stability of empty, half-filled or filled F subshell. Thus, the formation of cerium +4 is favored by its noble gas configuration. This question may be asked, guys. Please note it down. Cerium +4 oxidation state. This may come. Okay? All right. Yes, but it is a strong oxidant reverting to the common +3 oxidation state. The E0 value for Ce+4, Ce+3 is +1.74 volt, which suggests that it can oxidize water. However, the reaction rate is very slow, and that is why cerium 4 is a good analytical reagent. Now, praseodymium, neodymium, terbium and dysprosium, they also exhibit +4 oxidation state, but only when they are forming oxides, okay, not otherwise. Only when they are in oxides form, at that time they show you +4 oxidation state. Okay? Alright, now europium 2+ is formed by losing 2 s electrons, and its F7 configuration accounts for the formation of this ion. But europium 2+ is a strong reducing agent because it changes to common +3 oxidation state. Similarly, if you have Yb2+, which is F14 configuration, it is a reductant. Terbium +4 has half-filled f orbitals and it is an oxidant. The behavior of samarium is very much like europium. It exhibits both +2 and +3 oxidation state. You guys are getting it, everybody? Yes. Okay, chalo. Now, apart from this, we do not really have many things here, but this is a very important diagram. Everybody, please go through this diagram once. Okay? Please go through this diagram once. All right? Yes. Yes, I have the old version of the book because the old version has much more details. That is why I have the old version of the book. The new ones hardly have anything. Yeah, we have to teach you something, isn't it? We have to teach you something. Guys, can you please answer Dharmendra? He is against spamming. He doesn't know the planning. He has come and now he is telling me what to do. Somebody please answer. Oxidant, yeah, you tell me. Something is an oxidizing agent, something is a reducing agent. Guys, come on, yeah, such basics. What are you asking, Kavi? What is an oxidant? Can somebody tell? Can somebody tell me what is an oxidant? Come on, yeah. Come on. Chalo. Now, the best single use of the lanthanoids is for the production of alloy steels for plates and pipes. A well-known alloy is mish metal, which consists of a lanthanoid metal 95%, iron 5%, and traces of sulfur, carbon, calcium, and aluminium. A good deal of mish metal is used in magnesium-based alloy to produce bullet, shell, and lighter flint. Mixed oxides of lanthanoids are employed as catalyst in petroleum cracking. Some individual lanthanum oxide are used as phosphorus in television screen and similar fluorescing surfaces. Okay? Yes, everybody. All right. Very good. Now we go to actinoids. Actinoids, there will be hardly any question, but still I will tell you some of the electronic configuration that you must see. That is protactinium, uranium, neptunium, thorium, americium. Absolutely, you must go ahead and look at it. Curium, and then finally lawrencium. Okay, these electronic configurations you must know. Okay, these electronic configuration you must know. Okay, and बाकी तो same ही है. Electronic configuration is very similar to that to that of lanthanum. Ionic sizes, you all know that they also have a M3 plus ion, and because of actinoid contraction, what happens? They have very small size. Yes, they will be very small size. Oxidation state, you all know. Here you can see the oxidation state as well, right? Most common oxidation state, however, is +3, everybody. Okay, all right. The general characteristic and comparison of lanthanoids is also given, that you just study once, that you just read it once, guys. I think I'm losing my patience now. And some applications. That's it. We are done with the DNF block chapter, guys. Okay. How will be the question? Yeah, I will show you. Wait, I'll show you one question for this potassium permanganate and dichromate. I have a question. I have a question here. Here, this is how they're going to ask you. Describe the preparation of potassium permanganate. How does the acidified permanganate solution react with oxalic acid? Write the ionic equation for the reaction, everybody. This is how you're going to do it. This is how you're going to write it, okay? Describe the preparation of potassium permanganate. You know where to find it? Yes. Potassium permanganate. How do you prepare it? You take MnO2. You take MnO2. Yes. Then what do? You can fuse it with KOH and KNO3. Isn't it? Yes. Then you will get MnO4 minus, right? Then after that, what do? You have to do electrolytic oxidation, and then you will get K2MnO4. That's it. That's the preparation. After preparation, now you have to write acidified permanganate solution. That means, see, MnO4 2 minus we will take, and oxalic acid is what? Oxalic acid is C2O4, H2C2O4 2 minus. So C2O4 2 minus. From here, what will you get? You will be getting carbon dioxide. Yes, you will be getting carbon dioxide, plus you will be getting Mn in 2 plus, right? And what else will you be getting? Here you will also have to write H2O. How many H2O? There are 4 oxygen here. So initially, let us try and write here 4 hydrogen also. Okay? But this also we have to balance. CO2 you have to balance. C2O4 2 minus you have to balance. All you have to do is just balance it. That's it. Here is the reaction also. Here the reaction is also given, guys. The reaction is also given here. See. That's it. Yeah, you have to balance it. Joe, you will have to balance it. You will have to balance it. Yes, you must balance it actually. Okay, so this is the kind of question that you will be getting, and this was the PYQ. Okay, now once again, see, write the steps involved in the preparation of K2Cr2O7 from NaCrO4. This we know. This we know. How do we do it? How do we do it? See, Na2CrO4. Yes. Then what will happen here? H plus. H plus. You will be getting Na2Cr2O7. Yes. Then you will take Na2Cr2O7 plus. Sorry. Here what will you do? Here you will add KCl and then you will get K2Cr2O7. Am I right? This is how you will be getting. Right? For KMNO4 from K2MNO4, that also I have just taught you, so you can write that also. Is that right, everybody? Now, let us take a 10 minutes break, everybody. Let us take a 10-minute break and then we will start with coordination compound. So I guess the evening session, I'll push it a little later. Okay? I will take the evening session also, but we will push it a little later. Okay? है ना? Can we have a break, guys? Dharmendra Bacha. Yeah. My voice is Dharmendra Bacha. No worries. Listen to me. We will do PYQ as well. See, there is only 4 days gap. A PYQ series is not possible. I will take 2 sessions for PYQ. I will take 3 sessions for PYQ, but a series is not possible. We are only going to do marathon and we are going to do PYQ. Right now also I am taking you through PYQs and I am taking you through the concept so that you are crystal clear. Hai na bacha? So yes, I will do PYQ. I am doing PYQ even in today's session. We will do a dedicated session for PYQ as well. Okay? But series right now is not possible. Okay, chalo guys, now we are going to, where are we going to get the PYQ? I'll be sending it to you in the Telegram channel. 10 minutes break, guys. 10 minutes break. 10 minutes, not more than that. Okay? 10 minutes, everybody. 15 minutes, no. 15 minutes, then but the next session will also get delayed. Now, we will take 10 minutes break. Okay? 10 minutes, please. 10. Acha, chalo, okay. 15 minutes break. Okay, 15 minutes break, guys. 15 minutes break. Chalo. See you in 15 minutes. I want you all to be back. Okay? Coordination compound we are going to complete. Yes, we will achieve our targets. Without a fail, we will achieve our targets. Chalo, bye. See you in 15 minutes, guys. 15 minutes. Bye. Hi everybody. Can you hear me? Is that so, Roshan? How was it? How was the exam? No. Anime and all is fine, but you know what happened in today's class. My God, today's class was uh, one circus only that happened in today's session. You know, I probably can still take abuse, but somebody telling me that I was talking about caste, I never do that. I never do that. That's not me. And then, I did not get triggered. I got scared because truly in India, talking about caste, it's an atrocity. Many people do it, but I guess I am educated and I was taught better by my parents. So when that happened, I actually lost my mind. So that just happened. Manoj, like I said, I did not get triggered. I got very scared because, like I said, that atrocity, it's a non-bailable offense. So if somebody tries to actually, put me in a jail, then I cannot get even a bail. I can never come out of the jail. So without doing something, if I go to the prison and if I cannot come out, it's horrible. So I got really scared. I was about to cry. There was actually tears in my eyes, but I still somehow controlled, and I tried to take the session. So yeah, please do not do that. Yeah, if somebody does not talk about it, then please do not tell them that yeah you are talking about it. It's just really sad. All right, guys, I'm going to give you 2 to 3 minutes. Everybody quickly go and call up your friends because we are starting with coordination compound and we are going to finish it. Everybody, English exam ho gaya? Kaisa tha? How was the English exam? Yes, we are going to start now. Chalo. Now, coordination compound, guys, I am not going to go through NCERT because I have just seen that it takes a lot of time. And you guys anyway are not very interested, and coordination compound, it is my favorite chapter, my most favorite chapter. So let us everybody quickly go and start with the session. Yes, we are starting. Quickly go and go and start with our classes, everybody. Yes. Yeah, the evening class I'll be pushing it to 7 p.m. or 7:30 p.m. but yes, we will be completing it today. Okay? English was lengthy. English was lengthy, isn't it? मैम क्या बोले जाती है जो बोलने का मन करता है 90 plus in English, done and dusted. Awesome. That's a very good marks, I feel. That's like an amazing marks. Guess where I am from? I wish I had that much time. Just kidding. Okay, guys, so let us bring it on, everybody. Coordination compound. The session is going to be now easier because we are done with the DNF block. We have started from the basics of DNF block. We literally pulled it to the PYQs, isn't it? And now coordination compound. So everybody, you must have understood, or you must know about the difference between double salt and coordination compound, because that is the first thing that you are supposed to do. Okay, that is the first thing that you are supposed to do, everybody. Now, in the chapter of coordination compound, the first line that talks about, the first line in your NCERT that talks about coordination compound says that actually coordination compound is not something that is new. Coordination compound has always existed. Yes, coordination compounds are basically your hemoglobin is a coordination compound, the chlorophyll is a coordination compound. All of these are coordination compounds, right? Now, just like coordination compound, there is also something that is called as a double salt. For example, let me give you an example of a double salt, everybody. Let's say that you have a double salt whose name is carnellite, okay? Name is carnellite. Now, if I write the formula here, it will be KCl, then you have MgCl2.6H2O, okay? If I dissolve this into water, okay, if I dissolve this into water, then I will notice that it will get completely dissociated. It will be showing the presence of K plus, Cl minus, Mg plus, Cl minus, and it will be showing the presence, each and every ion that are present here, it will be showing that presence. However, in case of a complex ion, that is when we are talking about a coordination complex, that is, let's say you have K4 here and then you have FeCN6, right? If this is the case, then you will see that even after dissolving it in water, this particular part of the complex, it will never ever show, it will never ever dissociate, it will never ever completely dissociate and show you the presence of the ions. Okay, it will only dissociate and show you that there is K4. K4 will dissociate and you will be able to see K4, but you will never be able to see FeCN6. Okay, all right. So double salt, there are many examples that are present in your NCERT book. For example, you have more salt, you have carnellite, right? So yes, more salt is a double salt, but K4 FeCN6, this is a complex ion. All right, everybody? Yes. Now let us understand some of the terminologies that are associated with the coordination complex. Shall we, everybody? Yes. Let us do that. But one second, guys. One second. One second, everybody. Okay? I guess I should have done this earlier, but this is not coming out. Chalo, no problem. I guess sitting is not there in my this thing. Yes, Roshan, very good. I'm so glad that you already know how to write the name. Yes, so glad that you already know how to write the name. Very, very, very good. Yes. Cyanidoferrate. Yes, it is going to be ferrate because I will tell you why it is ferrate, okay? I will tell you why it is ferrate. Don't worry about it. Alright guys, now let us talk about some of the terminologies that are associated with coordination complex. First of all, what is a coordination entity or a coordination sphere? Right here, my dear students, do you see this? This part is called as the coordination entity or coordination sphere. Okay, whatever you see outside, it can be either this side or it can be this side. Any of these ions that are outside the coordination sphere, they are called as counter ions. What is it called? It is called as counter ion. Then right here, do you see that there is Fe here? Fe will be called as the central metal atom. Okay, it is the central metal atom. And Cn that we saw, that is called as the ligand, everybody. Now read the definitions, everybody. Yes, the coordination entity or the coordination sphere, it constitutes a central metal atom or ion and ligand. What is the central metal atom or the ion? The metal atom around which a fixed number of ligands are bound. And what are ligands? Ligands are the neutral molecules, anions or cations, which are directly linked with central metal atom or ion in the coordination entity. Yes. Ferrate is right, bacha. Ferrate is right. Chill, Mari. I will tell you how to name it and everything. Don't worry about it. We will tell you. Okay? Alright. Now, what is coordination number? Coordination number, my dear student, is the number of sigma bonds between the ligand and the central atom. Or you can directly know it as the number of ligands that are linked with the metal atom. That is called as your coordination number. Okay? What is the oxidation number, guys? The oxidation number is basically counted. It is calculated for the central atom. And you can calculate it on the basis of what ligand, what is the charge that is present in the ligand, and based on that you can calculate what is the oxidation number of the central atom. Got it clear? Yes. Now ligands, there are different types of ligands, guys. There are ligands that are based on charge. Ligands based on charge can be divided into neutral ligands, positive ligands, and negative ligands. Okay. Which one's a neutral ligand? For example, you have aqua, that is water, and amine, that is NH2. NH2 is known as amine, everybody. AMMINE, that is your NH2. And water is H2O. Both of them are neutral ligands. Okay? Now you must have noticed positive ligand. You have NH2, NH3, which is called as hydrazinium. Hydrazinium is a positive ligand, and negative ligand you have Cn, you have On, you have SCN minus, right? These are the ligands which have negative charge and they are called as negative ligand. Now, based on denticity, as in how can you hold? For example, everybody, you know this book. How can I hold this book? I can hold this book like this with just one finger, right? With just one finger, I can hold this book, isn't it? So that means here, how many fingers am I using? I'm using only one finger. So I can say that the denticity is just one. Okay. Now, if I hold this book with three fingers like this, okay, with three fingers like this, then what is going to be the denticity? Denticity is going to be 3. If I hold it with all my hand, that is 5 fingers, everybody. That means it is going to be pentadentate, everyone. Yes, pentadentate. So do you understand what is denticity? Denticity is basically with how many teeth are you holding to the central metal atom, right? Okay. So based on denticity, you can divide the ligand into monodentate, bidentate, tridentate, tetradentate, pentadentate and hexadentate, everybody. Okay. All right. So this will be the denticity. This will be how we divide the ligand in based on denticity. Okay. So if a ligand is monodentate, that means they have only one donor atom. Okay. Shabari bacha, will you cover physical line by line? No bacha. Physical chemistry does not depend on NCERT so much. We will do the concepts. We will not be doing NCERT line by line. Okay. Yes, teeth is similar to bond here. Acha. Now everybody, I'm not very sure if we will be able to do physical chemistry because one, my voice is going down. Secondly, my legs are paining. And thirdly, I haven't had any food. So I sort of want to finish this class and take my food. Maybe tomorrow morning we will start again. Can we do that? Tomorrow morning we will start again with physical chemistry and tomorrow I will take 2 sessions. Okay? Can we do that? Would you mind? Because today we are done with your inorganic chemistry completely, right? Would you mind, everyone? I do need a little bit of rest, I feel. My back is paining, but tomorrow I'll be able to do it. I'll feel a little better as well. Yeah, of course I'll be sharing this PDF. Of course I'll be sharing this PDF. And we do not know for how much more time this will take because coordination compound is also slightly bigger chapter. Can we do it tomorrow morning then? Tomorrow morning, same time, 12 o'clock. 12 o'clock we will start and we will finish it by 3 o'clock. Physical chemistry is going to be short. Hannah? Okay, thank you so much. So today let's finish this. We will do that chapter tomorrow. Okay? Yes. Okay. Alright guys, now monodentate, everybody, monodentate, they have one donor atom. For example, you must have seen the anionic ligands such as F minus, Cl minus, Br minus, H2O. They all have only one donor site, right? They have only one donor site, guys, and that is why they are monodentate. No, bacha, for organic you have Nandini ma'am, no? Durgesh Nandini ma'am, right? She's gonna do that, yeah. Hey, 12 a.m. no, 12 p.m. to 3 p.m. Janardhan, Nandini ma'am, 10 a.m. 10 a.m. will be too early, Baba. I won't even wake up, Yasuvar. I will wake up, but I also have to make my food, eat my breakfast, and then I have to do it. No. Yes, Roshan, you must. Chalo guys, move on. Let's move on. Okay? Let's move on. Bidentate, guys. Bidentate, you know that they have 2 donor atom and they have the ability to link with the central atom with 2 position. For example, you have oxalato. See, oxalate can donate from this oxygen. It can also hold on to the metal from this oxygen. So 2 donor site. That is why it is bidentate. Okay? That is why it is bidentate. Okay? Alright, here also you see ethylene diamine, En. Ethylene diamine, see, nitrogen, one this side and one is this side. So there also you have two donor site. Okay? Alright, two donor site. Okay? Alright, everybody? Yeah. Which video private? Why will I make this video private? Sorry. You see, this is why I'm telling you that I need to rest. My body is not... How many lessons? This is the second lesson we are doing. No, I will not make any of the video private, okay? Yeah, I will ask Nandini Ma'am to do that. Pakka, I will ask to do that. Sorry. Hello Kishore. Chalo guys. Moving on. Then next we have tridentate, guys. Now if you look at tridentate, we have diethylene triamine. Please don't get confused. You have one that is ethylene diamine. This is diethylene triamine. See, you have one donor site this way, one donor site here, and there is another donor site here. So 3 nitrogen together, they can hold on to the metal. Okay. Yes, Kishore, what is your doubt? If it is related to inorganic chemistry, I will reply. Otherwise, I'll reply it in the next session. Okay. Yes. Moving on, guys. Then we have tetradentate. See, in the exam, they may ask you to write the examples of tridentate, tetradentate. So please take a look at it. Okay. Here, see. Tetradentate, you have 1 here donor side, 2 here, 3 here, and you have 4 here. So triethylene tetraamine is your tetradentate. Okay. Alright everybody, moving on, you have pentadentate. Pentadentate is ethylene diamine triacetate ion, that is EDTA minus 3. If you have EDTA minus 3, then it is a pentadentate. Otherwise, EDTA 4 minus is a hexadentate ligand. Okay. Alright. No, di-N and ENDT are same. No. Why? Ethylene no. How will it be? Diethylene triamine, di-in. No. Ethylene ethylene diamine triacetate ion, EDTA. What is the difference between chelate and didentate? I'll tell you, bacha. I will tell you. Don't worry. I'll tell you. Yes, Manoj. EDTA is basically a ligand. There is nothing much to explain, but understand when EDTA has minus 3 charge, it is going to be pentadentate. See how it can donate? It can donate from this O. So here, first position. It can donate from this position, second position. It can have this donor site, so third position. This O can also donate, so fourth position. And right here you have another donor site, which is your fifth position. Hence it becomes pentadentate. What does it become? It becomes pentadentate. Similarly, now if you have EDTA 4 minus, that is ethylene diamine tetraacetate ion, that is 4 minus, you will have 6 donor site. You have 1 nitrogen here, 1 nitrogen here, so 2. Yes, then you have this oxygen, which is third. You have this oxygen, which is fourth, everybody. Then you have another oxygen here, which is fifth here. And then you have another oxygen here, which is your sixth donor site. Donor site. That means these are the places from where electrons will be donated and the metal ligand bonding will happen. So guys, if you take EDTA 4 minus and if you want to make an octahedral complex, how many ligands do you need? I've asked you a very important and a nice question. Tell me, if you want to make an octahedral complex, and you have EDTA 4 minus, how many ligands will you take? How many ligands will you take? I'll send you the PDF, no bacha? You check it out then, okay? You check it out then. I'll send you the image, don't worry, you will be able to see the image. Yes guys, I'm asking you a question. I'm asking you the question once again, everybody. If you want to make an octahedral complex and the ligand that you have to take is EDTA 4 minus, how many ligands will you take to make an octahedral complex with ethylene diamine tetraacetate 4 minus ion? How many? Come on guys, everybody answer. What are you doing? What are you doing, guys? No one is going to answer? If you don't answer, shall I end the class then? I'll teach you half coordination compound. Guys, only one person has answered. What's wrong? Answer no. Ritish, very good. Yes, the correct answer is 1 because EDTA can hold on to the metal by 6 donor site. You will only need 1 EDTA ion to make an octahedral complex with a metal atom. Okay? Alright. Now here we have something that is called as ambidentate ligand. Ambidentate ligands are basically those ligands which can hold on to the metal atom from either of the side. That means, see, if you want me to, let's say that if I was, everybody, oh, 6 it seems, no, 1, it's a hexadentate ligand, right? It's an hexadentate ligand. So if you take it once, it will be able to cover it all up. 7 ligands it seems. Octahedral. Octahedral has 6. Guys, 1, 1, 1. You will take 1. Everybody, 1. 1. See, let's say that I want to pick up this book. I can pick it up with my right hand. I can also pick it up with my left hand, right? I can pick it up with one hand. I can pick it up with left hand, correct? So let's say that if this book is my metal atom. This book is my metal atom. So suppose a ligand is capable of holding on with the right hand or it can hold with the left hand. That is when an ambidentate ligand is there. For example, if you have Cn minus, then Cn minus can hold on to the metal with the nitrogen hand. It can also hold on to the metal with the carbon hand. And that is when you will get an ambidentate ligand. For example, if you have NO2, NO2 can hold on to the metal with nitrogen hand, or I can write it as ONO and it can hold on to the metal with the oxygen hand, right? So that is your ambidentate ligand. No, guys, art of cookies, anti-Nambi, unknown gamer, BGMI live, Vitesh, everybody. If there is an hexadentate ligand, you will take only 1 ligand to form an octahedral complex, guys. Art of cookies. Are I am telling you the answer. At least now change your answer. You need 1 ligand. One ligand, not 6. Since it is a hexadentate ligand, you will take only 1. If it is bidentate, to make an octahedral complex, you will take 3. If it is tridentate, then take 2. Okay, are you getting it? Now, let us understand chelating ligand. So, Sayyam was asking me, ma'am, what is the difference between didentate ligand and chelating ligand? See, a chelating ligand is always a polydentate ligand. That means 6. Are baba? You guys are saying anything that you want, huh? Somebody says 1, somebody says 8, somebody says 6, somebody says 4. Wow. But I have told you the answer. It is 1. Okay, take it. Anyway. Moving on, guys. Chelating ligands are always polydentate ligand. Now, what happens in a chelating ligand is whenever you use a chelating ligand, they form a ring-like structure. So, whenever you have a polydentate ligand, basically what happens is, try and understand this, guys. See, if I want to hold this book, with just one, like, with unidentate ligand. If I want to hold this book with unidentate ligand, with just one, then see what is happening here. Then see what is happening. Is it forming a ring? No. But if I want to hold this book with 2 fingers, see, now do you see that it is forming a ring here? Do you see that it is forming a ring here, guys? Do you see that it is forming a ring? This is exactly your chelating ligand. This is exactly your chelating ligand. So when a polydentate ligand is bonded with metal atom from 1 or more donor atoms, then the resulting structure is a 5 or 6 membered ring structure. That's when the ligand is known as chelating ligand. Are you getting it? Yes, I am. Do you understand this, everybody? Yeah, I think so too. The chat was reaching me later. Yes, I am getting the charts a little later. But now, do you understand this, everybody? Do you understand this, guys? Yes or no, people? Yes, guys? Do we understand what is chelating ligand? Somebody had asked, Sayyam had asked me. I think I remember his name also. Anyway, now moving on, we also have complexes. There are different types of complexes. Now you have cationic complexes, you have anionic complexes, you have neutral complexes, you have homoleptic complexes, and you also have heteroleptic complexes. Okay? Alright, now what are cationic complexes? The cationic complexes are those that have a positive charge with them. For example, CrNH3 plus here, see? CrNH3 plus, because it has a 3 plus, that is positive charge, it will become a cationic complex. Okay? Now what is anionic complex? If something carries a negative charge, that means see FeCN6 minus, do you remember that K4 FeCN6? K4 FeCN6, at that point of time, what did we write? Ferrate we wrote. Why? Because that was an anionic complex. Yes, because that was an anionic complex, everybody. Okay, moving on. Then you have a neutral complex. For example, NiCO4. NiCO4 is considered to be a neutral complex because it does not have any charge whatsoever. What is homoleptic complex? When all the ligands that are attached to the metal atom are same. That's when we have homoleptic complex. And what is heteroleptic complex? When all the ligands are different, present with the metal atom, then we call them to be heteroleptic complex. Cool, guys? Got it, everybody? Yes? Is this clear? Everyone, is this clear, everybody? Yes or no, guys? Yes or no? Yes? We are clear, right? We are clear with it? Chalo. Moving on from here now. Now let's check out how do we name an entity. Okay. Let us now check out how do we name an entity. Like how to name a coordination compound, because this type of questions will definitely come and you will see it right now. Okay. First rule is that you will always name the cation first in both positive and negative charge coordination compound. For example, if you have, let's say, K4 FeCN6, yes, what will you name first here? I've just told you that you always have to name the cation first. Here, which one is the cation, guys? What is the cation here? The cation, my dear student, is your potassium. So you will write potassium first. Always you will write potassium first. Okay? Secondly, then you will start naming the ligands in an alphabetical order, and according to the name of the ligand, not by the prefix. If you have bi and tri, if you have di and tri, do not go and start naming the di first. You always have to make sure that if it is aqua and cyano, then you are going to name aqua first, then cyano. Okay? Alright? Ma'am, if asked in exam, can I write two or more ligands which are different? Each in one complex is called heteroleptic. Is that right? Heteroleptic complexes are this. Metal is bound to more than one type of donor group. That's it. Metal is bound to more than one type of donor group. That is your definition, and this is what you are going to write. Okay? Yes, so you are going to write potassium first. Now, because you have homoleptic complex here, that means all the same ligand is attached. So you are now going to start writing as hexacyanido or cyano. Hexacyano. Write hexacyano. Okay? Hexacyano, then you are going to write here ferrate. Why? Because the complex itself is a anion, and if the ligand here is anion, if the ligands have a negative charge, that means, you know, let's say you have Cl, so chlorido, fluorido, cyano, oxalato, right? That is how you are going to write. Okay, that is how you are going to write. All right, everybody? Yes. All right, everybody? Aqua first, then cyano. Yes, aqua first, then cyano. If you have a cationic ligand, for example, hydrazinium, remember? Hydrazinium, nitrosonium, yes, when you have NO or N2O plus, that time you write nitrosonium, yes, so ium suffix has to be added if you have a cationic ligand. And if there is a neutral ligand, no suffix, no prefix is needed at all. Okay. Now, Let's say if you have number of ligand 1, then you are going to use the prefix mono. If you have 2, then di. If you have 3, then tri. If you have 4, then tetra. Then 5, then penta. And 6, then hexa. That is why what we were writing hexacyanoferrate. Okay? Yes. Now, if you have a ligand, for example, like ethylene diamine, or you have EDTA, ethylene diamine tetraacetate ion. See, tetra is also there, diamine is also there. Now what are you going to do? If there are, let's say, if there are two diene, if there are two diene, because in the name itself you have di, or if there are 3 diene you are taking, then you have to add tris, bis, tetrakis or pentakis. Okay, like that you have to use. Okay, like that you have to use. For example, let's say that if we take this ligand, okay, if we take this ligand called as let's take this ligand diethylene triamine. Okay, this is a tridentate. So let's say that we have CO diene 2. How are you going to name it? You are going to name it as bis diethylene triamine cobalt and then oxidation state. Getting it? Yes. Now do you understand? When to use this bis, tris, tetrakis, pentakis? Yes. Now do you understand? Somebody had asked, no, ma'am, when to use this? This is when you use it. Okay, this is when you use it. Okay. Yeah, funny prefix, I know, but this is what you use. Okay. All right, guys. Moving on from here. Now, when you want to name a mononuclear coordination compound, let's say that you have an ambidentate ligand. Okay. So let us take the example. I always take this example because I really like it. Let's say that we have pentachloro. We have pentachloro nitrito. Yes. Kappa N. Okay. Nitrito kappa N cobaltate 3. What does this name mean? This name means, everybody, sorry. This name means that pentachloro, so you have cobalt here 1, 2, 3, 4, 5 and 6, right? 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5 and 6 here. So that means that you have Cl here, Cl here, Cl here, Cl here, Cl here. But see, kappa N, that means what is happening is you have nitrogen, oxygen and oxygen, nitrito. This is what it means. But suppose everybody. Now I have another compound which is named as pentachloro nitrito kappa oxygen cobaltate 3. What does this mean? This means that you have cobalt, you have 1 Cl, you have 2 Cl, you have 3 Cl, you have 4 Cl, you have 5 Cl, and the 6th one you have ONO. Are you getting it? Are you getting it, guys? Yes. So this is what it means, and this is how you write the ambidentate ligand name. Now this is the actual IUPAC rule. This is the actual IUPAC rule. In a lot of places you might not see the usage of kappa, but trust me, mark my words, this is the actual IUPAC rule, everybody. Okay? All right? Yes. So Kritis is asking, what is the difference between amine and amine? But amine means NH2, amine is NH3. It is a ligand that is used in the coordination complexes, and make sure that you always write both the M in the spelling of amine. Do not leave out any of the M. Okay? Marks will be deducted. Please make sure that you write that. Okay? Next, guys. Now you also have to find the oxidation state of central atom, and that should be written in Roman numeral in parenthesis. Okay, you must always find out the oxidation number. Okay. Alright, now if you have a cationic complex, then no suffix, no prefix. If there is an anionic complex, then you are going to add the suffix ate. Alright, yes, of course I know Shimon sir. Why won't I know Shimon sir? Yes. Diksha Bacha, we will do the, can't we just write it as O nitrito? Yes, you can, Ritis. Yes, you can. That is what I told you, right? That using the kappa is the actual IUPAC nomenclature. However, in many of the cases, you do not see the usage of kappa at all, because I think over the years, they have just made it a little more convenient for ourselves. We have just made it a little more convenient. But the correct IUPAC rule says that you have to use kappa. You have to use kappa. Okay? Alright? What is the structure of chlorido triphenyl phosphine palladium? You find out, no? What is the structure? Diksha, we will take the physical chemistry class tomorrow morning, okay? Tomorrow morning from 12 o'clock to 3 o'clock, we will finish it, okay? Okay. If there is a neutral complex, then there is no suffix at all needed. And now, naming of mononuclear coordination entity, guys, there are certain, there are certain metals for which you use when they are in the anionic form, okay? In the anionic form, then you have to use the Latin name. What is taught in your school? If in your school they have taught you to use kappa, then use kappa. If they have not taught you how to use kappa, then don't use it, okay? Then write it as O nitrito, N nitrito, okay? Alright? Tomorrow we will do physical chemistry, yes. Now guys, have a look at it. If you have iron, then the cation or the neutral state of iron will be written as iron. But in the anionic form, you're going to write ferrate, okay? If you have silver, for cation or neutral, you are going to write silver. But if you have anion, then you're going to write argentate, okay? Similarly, if you have gold, then you're going to write gold here. Otherwise, you are going to write here aurate, okay? If you have lead, then you're going to write lead for cation or neutral. For anion, you are going to write here plumbate, everybody, okay? Finally, for SN, you are going to write here tin, but otherwise, you are going to write here stenate, everybody. Cool, guys? Yes, yes, yes. Nambi, what happened? What happened? Yes, this is clear. And now guys, here right in front of you, I have a cheat sheet. Please print it and study it as much as you can today and tomorrow. This is very important. You will be able to get all the ligand name, and from here you can practice. Okay? So you have all the monodentate, all the bidentate, all the neutral ligand, and all the -1, that is the negative ligand. All of it today only you will be able to finish it. I thought that we will complete physical chemistry. Yes, Gayatri, I thought so too. But see, I have been taking a class from 12:30 and it is already 5 o'clock. So 12:30, 1:30, 2:30, 3:30, 4:30, 5:30 it is going to be. And I guess I'll be able to complete the session by 6:30. So that means I am already taking a 7-hour session. Please understand, I'm not a robot. I'm also a human being. Beyond 8 or 9 hours, it gets very difficult. So that is why I don't think I'll be able to speak tomorrow if I take more than 7 hours. Also, my legs are paining. Can you understand? Since the last 5 hours, I'm standing right here. I'm standing right here. I haven't moved from here. So it gets very difficult. My legs will swell up. I'm already not well. I haven't eaten anything. Yes, since morning I haven't eaten anything. So that is why I'll have to give it a break today. I'll take the next class tomorrow. Okay, Gayatri? Thank you so much. I really hope you understand me. Now guys, let us solve one or two questions that are related to nomenclature. Okay, let us solve 1 or 2 questions that are related to nomenclature, everybody. Here we have the questions. Chalo. Now, what should I focus on first if I need to start everything? The whole 10 chapters. As I've watched your session, I've covered 2 chapters now somewhat. What about the rest? The rest 3 chapters. So 5 chapters I'll be completing. The rest of the 5 chapters will be taken by Nandini Ma'am. Okay? She will be taking it. Okay? She will be taking it. Thank you, Shayoni. Thank you so much. Okay, guys, let us solve this. Write the IUPAC complex. Write the IUPAC name of the complex. How do we write it? We will be writing it as how? Dichlorido, yes, then bis ethylene diamine cobalt, yes, then write the oxidation state. So how do you calculate the oxidation state? You will write here X plus Cl has -1 charge, so 2 -1. En, ethylene diamine. Guys, in the cheat sheet it is written that ethylene diamine. What is ethylene diamine? Does it have any charge? Does it? RDX gamer, what are you writing? No. Why? Why will you do that? See guys, here it is. Ethylene diamine, everyone. Ethylene diamine is a neutral bidentate ligand, okay? It is a neutral bidentate ligand, everybody. So here we are. That means it has no charge. So 2 into 0 is equal to, do you have any charge here? Yes, you have +1 charge here. So X minus 2 plus 0 is equal to +1. That means X is equal to -3. No, +3, right? That is the oxidation state. So all you have to do is write 3 here, and that's it. That's it. Yes, that's it. Cool? Cool, everybody? Yeah? Cool, guys? Understood? Thank you so much, Harish. Thank you so much. Chalo, guys. Okay, next. Write the IUPAC name of the complex CONH3,4ClNO2. How do you write it? You are going to write here. Tetraamine. Yes. Chlorido nitrito. No, chlorido nitrito cobalt. Yes. And then if you again calculate, this is going to be 0. This is going to be -1. NO2. NO2 has what charge, guys? NO2 has what charge, everybody? NO2 has what charge, everyone? Again, you can refer to the cheat sheet. You can refer to the cheat sheet. Here you have. Where is NO2? NO2 has C. Nitrite has a negative charge, isn't it? Negative charge, 1 negative charge, everybody. It is a monodentate, -1 negative charge. So here how are we going to calculate it? See, -1. This is also -1. And here this is equal to +1. So +1, +1, +1. That means once again 3. This is how we calculate it. This is going to be the answer. Right? Right. This is the answer. Yes? Yes? Okay. Very good, guys. Very good. Now, next one, everybody, let us see. Using IUPAC norms, write the formula for the following. You have sodium dicyanidorate. See, what do you have? You have sodium, so Na. Yes. Then what do you have? You have dicyanido. So Cn, you have Cn2. Okay. Then you have orate. So here you have gold. Yes. Then what do you have? Dicyanidoorate. So yes, Cn2 orate, and here you will write plus. Yes, this is going to be your IUPAC formula. Correct? Next, guys, next one. Check it out. Tetraamine chlorido nitrito N platinum 4 sulfate. Acha. So you have platinum, that means Pt. We are writing it down. After Pt, what do we have? You have tetraamine. So NH3,4 chlorido 1Cl nitrito. So NO2 like this. Yes. And then you can write here SO4, but here you can write +4. Got it, guys? Clear? Yes? Clear? Yes? Yes, no. Senthil, whenever you have a negative ligand, a cationic ligand, then you put the IDO, okay? Otherwise, no. Only then you will be putting it, okay? Not otherwise. Chalo guys, next. Using IUPAC norm, write the following formula. Will you all be able to do this now? Put N near platinum. Rear. Bacha, you missed it out. But why are you doing this, yeah? Why are you doing this? What did I tell you? Nitrito, it is an ambidentate ligand. Either it will hold on to the metal with the nitrogen hand or it will hold on with the oxygen hand. If it is holding on to the metal with the oxygen hand, then you will write oxygen first. If it is holding on to the metal with the nitrogen hand, then you are going to place N near platinum. I've just told you, rear. Rear and Madan, I have explained it. Okay? This I believe that you will be able to do it. So giving this to you as homework. Okay, I need you guys to solve it. Write the IUPAC name of the following. I believe this also you will be able to do it. The answers are right there. You can check it out. Okay. So basically most of the practice questions are based on IUPAC. Yes. And here now guys, specify the oxidation number of the metal in the following coordination entities. Can you specify the oxidation number? Shall we do it, guys? Shall we do it? Chalo, here see. For cobalt, X, H2O is neutral, so that means 0. Cn has -1 charge and En has how much charge? En has what charge, guys? En has what charge? Very recently we have done, guys. Recently we have done. We have just covered it. En has what charge, everybody? En has what charge? En has what charge? No one is telling. En has 0 charge. En has a 0 charge, everybody. Yes. What are you guys asking? No, if there is nothing, then we assume that it is going to hold on to the metal with the nitrogen hand. Okay? We assume that it is going to be nitrito N. Nitrito N. Yes. Nitrito N. Nambi, how much time will you ask me the same question, bacha? Nandini ma'am will take the evening section. She will. Okay? Chill. I've told you she will. I will ask her that. Okay? Yes. En again has 0 charge, so +0, and here you can see that the overall charge is +2. So this -1 will also go. That means X is equal to +3. So cobalt is in +3 oxidation state. Okay? Cobalt is in +3 oxidation state. Okay? Alright. Similarly, now if we go for cobalt here, Br2, bromine has negative -1. So 2 multiplied, En has 0 negative charge, and here is a +1. So that means this will also become +3. Okay, this is how you calculate for oxidation state. Now, shall we move on towards valence bond theory, everybody? Can we move on towards the valence bond theory, everybody? See, valence bond theory, if you want to understand in an absolute layman term, okay? If you want to understand valence bond theory in an absolute layman term, understand this and listen to me. One sentence, I think you will be able to understand. Okay, what is valence bond theory, guys? What do you do? The metal, yes, the metal has 3d orbitals, it has 4s orbital, it has 5d orbitals, it has 4d orbitals, right? Right, everybody? Now, when the ligand is approaching, the metal realizes that, oh, some of the rooms that I have, they are bigger, some of the rooms that I have, they are smaller, right? Yes, yes, everybody, correct, everyone? Now what will happen is, everybody, this ligand, when it is approaching, so the metal realizes that, oh, the ligands are approaching, the ligands are the guest, I have to give some rooms to the ligand. So the metal will empty its orbital. The metal will empty its orbital, it will hybridize it, and then it will give it to the ligand that, yes, come and fill up your electrons. Getting my point? What did I say? What did I say, everybody? According to this theory, the metal atom or ion under the influence of ligand can use the n-1d, ns, np, or it can use ns, np, nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry, and these hybridized orbitals are allowed to overlap with ligands orbitals that can donate electron pairs for bonding. Now, did you guys understand? Should I tell you this again? Should I tell you this again, everybody? Once again, I'm telling you. So the metal has vacant orbitals. It has d orbitals, s orbitals, p orbitals, right? Right, everybody? Now, 3d, 4s, 4p, they have different energies, right? They have different energies, right? So imagine if the ligand is coming and the ligands, okay, so let's say, everybody, let's say that you guys from your school, if you're going for a picnic, yes, if you're going from your school for a picnic, all the students must get the same kind of room. If somebody in your school, they get a hotel room with bathtub and nice balcony, nice view, and somebody gets a chotu room where there is not even a bathroom, what will happen? Fight will happen. Fight will happen. Yes. So similarly, when this ligand is approaching the metal knows that Are Baba, ligand is coming, and all of these ligand, they will want the same kind of room. So what do I do? What do I do? What do I do? It will quickly empty its orbital. Then it will hybridize, make it all equal, and then it will give it to the ligand that go, fill it up. Getting it? So now, if you all are going for a picnic, then your class teachers, your principal, they will make sure that each and every room is similar. Each and every room is similar, isn't it? They will make sure that all of you get the exact same room so that nobody fights. This is exactly what the metal is doing. Understanding? Yes, so this is your valence bond theory, guys. Now, valence bond theory for octahedral compound, they can form two types of complexes, which is called as outer orbital complexes or inner orbital complexes. In case of inner orbital complex, you use the 3D, okay? In case of outer orbital complexes, you use the 4D orbital, that is the next available d orbital. In case of inner orbital, pairing up happens and you use the inner d orbital, okay? Inner d orbital. Cool, everybody? Yes? Yes, everyone? Yeah, absolutely, Habib. Bathroom is very important. Yes. Yes, guys. Do we understand this? Very good. Now, for coordination number 4, okay? For coordination number 4, they can either form sp3, that is tetrahedral complexes, or they can form dsp2, that is square planar complexes. Now, if they form sp3, then it is going to be outer orbital complexes, and if they form dsp2 complex, then it is going to form inner orbital complex. Okay? Yes, mostly the inner orbital complexes, they are of low spin. What is low spin and high spin? Understand, bacha. When they are forming inner orbital complex, that means the electrons are paired up. If the electrons are paired up, they can't spin properly, right? While spinning, they have constraints, right? But when they're forming outer orbital complex, pairing up has not happened. So that means one electron in one box, they can spin now like this. They can spin. So high spin. This is high spin and this is low spin. When they're paired up, low spin. When they're not paired up, they have high spin. Are we understanding, everybody? Is this clear? Yes. So the outer orbital complexes, they are generally paramagnetic in nature, and the inner orbital complexes generally are diamagnetic in nature, or they are, we can say, less paramagnetic in nature. Cool, everybody? Yes, Nambi. Very good. Now we come across crystal field splitting, everybody. In case of crystal field splitting, what do we see there? There are certain postulates, okay? There are certain postulates, everybody. Yes, Kavi, you are right. So in crystal field splitting energy, what we noticed was that in here, the metal and the ligand bond is ionic. It is considered to be ionic here. The ligands are treated as point charges here, okay? The ligands are treated as point charges here, and in case of anions or dipoles, in case of neutral molecules, yes, what happens is the ligands are treated as point charges in case of anions or dipoles in case of neutral molecules, right? But that's not the case. Ligands can be F minus, ligands can be Cl minus, Br minus, it can also be H2O and ethylene diamine. How can you consider ethylene diamine or EDTA4 minus as a point charge? Can you do that? Can you do that? You cannot do that, right? You cannot do that, guys. So this postulate was proven to be wrong later on. That's how we moved on to molecular orbital theory. The 5 d orbitals in an isolated gaseous metal atom or ion, they have the same energy. That is true. Yes, they are considered to be degenerate, right? Secondly, because of this unsymmetrical field of ligands, the degeneracy of the d orbital is lost, and that's when we get a splitting, right? That's when we get a splitting, isn't it? And finally, the pattern of splitting, it depends upon the nature of the ligand, nature of the crystal field, everybody. Yes, guys? Do we understand? So how does the crystal field splitting in octahedral coordination entities happen? Please make a note, everybody. In case of octahedral complexes, T2G is at the bottom, okay? T2G is at the bottom and EG is at the top. Okay? All right. Yes, this is how the splitting happens. But if you have a tetrahedral complex, then this splitting is ulta. You have E at the bottom, T2 at the top. And please make sure that do not mention G or do not mention T2G or EG for tetrahedral complexes. For tetrahedral complexes, G means Gerard, and this Gerard is only attributed for the symmetry that the octahedral complexes hold. Okay, the symmetry is only for the octahedral complexes. That's when you are going to use T2G, EG. Otherwise, you are not going to use it. Okay. All right, you do not have to memorize the postulates, but you should know. Okay? All right, yes, everybody, do you guys understand? Now, if the ligand is a weak field ligand, then the crystal field splitting will be less. If the ligand is a very strong field, then the splitting will be more. Okay? All right. Now, everyone, do you see here that 3 by 5? What is 3 by 5? See, the EG orbitals, they went up. But in comparison to who? In comparison to this 3T2G. Hence, we are writing 3 by 5. This T2G orbitals, they came at the bottom. But in comparison with who? In comparison with the 2 EG orbitals. That's why we write here 2 by 5. Now, if you calculate 2 by 5 and 3 by 5, you will find the values to be 0.4 and 0.6, and that is exactly what it means, everybody. Do we understand this, guys? Yes, do we understand this? Do we understand this? Yes, this is your energy separation. Then we come across something that is called a spectrochemical series, and we can arrange the ligands, okay? We can arrange the ligands as strong field ligand or weak field ligand because of this spectrochemical series. In the spectrochemical series, we have I minus, Br minus, SCN minus, Cl minus, S2 minus, F minus, OH minus. These are all in the weaker section. Whereas this side, if you see, you have H2O, NCS, EDTA, NH3, EN, CN, CO. CO is the strongest ligand possible, okay? CO, carbon monoxide, yes? Metal carbonyl that we studied, that's carbonyl, this is the strongest ligand, okay? How do you remember it? The trick is that the halide donors, that is F minus, Cl minus, Br minus, I minus, they are the weakest. Then wherever you have oxygen donor site, that is the second weakest. Then you have the nitrogen donor site, and the carbon donor sites are the most strong. Okay? The carbon donor sites are the strongest that is possible. Now, how did we come across this spectrochemical series? We came across this spectrochemical series based on some experimental observations. Okay? Based on some experimental observations, we have come across the spectrochemical series, and we noticed that the strong field ligand, they usually absorb the high energy as in smaller wavelength, okay? Whereas the weak field ligand, they actually absorb the lower energy, that is bigger wavelength or longer wavelength, okay? Longer wavelength is absorbed by the weak field ligand. Got it, everybody? Okay. Now, what happens is in octahedral complexes, okay, in case of the crystal field theory, in octahedral complexes, when you have a weak field ligand, okay, listen to this story, everybody, listen to this story. I believe that you will be able to understand weak field ligand. What happens? Imagine after completing your class 12th and everything, let's say that you are going to go to your hostel, right? Now in the hostel, once you go to the hostel warden, they are going to tell you that beta, all the, you know, all the ground floor are occupied by one student. Do you want to share it or do you want to go upstairs? Yes, do you want to go upstairs or do you want to share it in the downstairs? Your next question will be, sir, do you have lift? If you have lift, then you don't mind going to the upstairs rooms, right? But if there is no lift, then you will be like, I don't want to go to the 4th floor. Every time I'll have to climb the steps. I'll take the ground floor one only. Similarly, here is what happens. When there is a weak field ligand, the weak field ligands, they are not able to pair the electrons. So normally what happens is the pairing energy is higher. The pairing energy is higher. And that is why what happens is, because of the pairing energy being higher, delta octahedral, what happens is they do not pair up. They're all single electron. And when there is single electron, they form high spin complexes. But if the pairing energy is lower, and the crystal field theory, what happens is when you have a strong field ligand, they try to push the electrons, they try to pair them up, the pairing energy is now less. At this point, you will have low spin complexes. Guys, are we clear with this? Guys, are we clear with this, everybody? Yes or no? This thing, analogy. You get it, everybody? See what I was telling you about tetrahedral. See, in case of tetrahedral, we have only written E and T2. Why? Because I told you that the G is attributed to a German letter called Gerard, which is only applicable when there is the octahedral symmetry. Got it? Yes? Clear. Okay. Now, hybridization of NiCO4. This has come very many times in the exam. I suggest that you go through this page, everyone, okay? Once I'm done with this, I'll give you the PDF in the Telegram channel. Please go through it, okay? Please go through it. Now, similarly, another example is noted down here, which is CONH36, okay? CONH36 has been noted down for you. And this also you can go through, and please have a look at the hybridization. They may ask you about hybridization and the Bohr magneton. Okay? Now, magnetic properties of coordination complex, everyone. Similar to the DNF block, here also the magnetic moment is derived by the same formula, which is mu is equal to n multiplied with n plus 2. Okay? N multiplied with n plus 2. That this is how you calculate the Bohr magneton. The unit is also Bm, and n means number of unpaired electron. All right, everybody? Yes. Color of coordination compound. Once again, guys, why do you get to see it? You get to see it because of DD transition. Okay, the color of coordination complexes are noticed because of DD transition, everyone. In case of TiH2O63 plus, you get to see a beautiful violet color in the octahedral complexes. Okay, all right, everybody. Guys, are you listening to me or are you discussing about your own school? Huh? How will I know, Gokul, if it is going to be tough? I'm not the one who prepared the question. No, I do not know. Okay, now guys, this is important. Stability of coordination compound. This is there in your NCERT as well. Okay. The factors that affect the stability of complex ions. Stability is greater when the charge of the metal ion is greater. Okay. For the divalent ions of the first row transition element, irrespective of the ligand involved, the stabilities, they vary in Irving-Williams order. This is the order, everybody. This is called as the Irving-Williams order. See, Mn2FeCONiCuZn. This is the order, everybody. Now, manganese has a lesser stability than iron. Iron has a lesser stability than cobalt. Cobalt has a lesser stability than nickel. Nickel has a lesser stability than copper. But Copper has more stability than zinc, everybody. Okay? All right. Yes? Okay, guys. Okay. All right. Moving on. Smaller the size of the ion or greater the charge density on the metal, greater is the stability of the complex. Okay? What does it mean? It means that whenever you have a complex, if the size of the ion is if the size of the ion is smaller, and if the charge density on the metal atom is greater, that's when you are going to have more stability. For example, in ligands such as F minus, Cl minus, Br minus, I minus, F minus, it forms the strongest complexes. Why? Because F minus has a very small size, right? It has a very small size and higher charge density, correct? It has a higher charge density. That is why you will see that F minus forms better stable complexes. Now, stability also depend on the formation of chelate rings. The stabilization is because the chelation is called the chelate effect. So, whenever there is a chelating ligand, that time it will form a more stable complex. Okay, it will form a much more stable complex. Cool, everybody? Yes. Now, apart from this, during the stability, there is also something called as effective atomic number. Okay, what is it called? It is called as effective atomic number. So, this effective atomic number, guys, let us talk about this. But before that, let's understand one more thing. See, for the overall reaction, how do you form a metal and a ligand complex? This is how you form. Let's say that you have MH2ON, right? This is the ligand. Plus you have n number of ligand here. So finally what do you get? You get m number of m is the metal, and n number of ligand, they attach it themselves to the central metal atom, and water is out, right? Water is out, everybody. Correct, everyone? Yes. Correct, everybody? Yes. Now the above overall reaction, this reaction obviously does not happen in just one single step. What do you think? Does this happen in one single step? Obviously no. It will be happening in several different steps. For all these steps, there will be different stability constant, right? Do you remember in thermodynamics, in chemical kinetics, we have studied about constants, right? Equilibrium constant, yes, Kc, Keq, Kp, right? We have studied about this. So here also you are going to take different stability constants like K1, K2, K3, Kn. For each step you will take it, right? Now for the first step, let's say that you will have K1. For the second step, you will have K2. For the third step, you will have K2. And finally, you will have Kn. So together, if you add all, if you multiply K1, K2, K3, Kn, then you will get something that is called as beta n. This beta n, this, my dear student, is your stability constant, and this is obviously related to thermodynamic stability when the equation has reached equilibrium. Is this reaction important? Not at all. Okay? Not at all. Yes, this is not at all important, but you should know how to write it if they ask you. Now guys, let us quickly take a look at the effective atomic number. Okay, effective atomic number also suggests about the stability of coordination number. So we notice that when the EAN, that is effective atomic number, how do you calculate it? You calculate it as number of electron, okay, number of electron present in the metal atom, okay, number of electron present in the metal atom or the ion, plus number of electron donated by ligand, okay, number of electron donated by ligand, my dear student. Okay, all right. For example, let's say that if you have CONH3 6 CONH3 6 Cl3, okay. In this case, cobalt is in +3 oxidation state. If it is in +3 oxidation state, that means cobalt's atomic number is going to be 24 at +3 oxidation state, right? At +3 oxidation state, it is going to be 24. Now 24, 6 ligands are there, which will be donating 2 electrons, 6 into 2. So that means 36. Now 36 is a noble gas configuration, isn't it? 36 is a noble gas configuration. That means that this is going to be stable. If by chance you do not get a noble gas configuration, that means that that coordinate complex is going to be not stable. Notes maker, can you please stop spamming? I've seen your message, bacha. Not right now, please. Can you see that I am teaching something? Why are you disturbing me from the session? Huh? Why are you disturbing me from the session? I've seen your message, I'll do it, but not right now. Right now you can see that I'm taking a session, right? Yes, that's it. Gayatri, you do not need to learn the mechanism. Whatever I'm telling you, that is important. Note that down. Okay? Note that down. Okay? Where is S? I do not see any S. Okay. So stability, did you guys understand, everyone? Stability, did you guys understand, everybody? Yes, is the stability an effective atomic number? Is this clear to you all? Now let us quickly go through isomerism. Okay? Now isomers, basically what are isomers? In your coordination, in organic chemistry also you must have read about isomerism. So isomers are basically those two or more compounds that have the same chemical formula but they have a different arrangement of atoms. So they differ in one or more physical or chemical properties. Okay, bacha? All right, everybody. So here there are two different types of isomerism. One is called as your structural isomerism and the other one is called as your stereoisomerism. There are two types of stereoisomerism: geometrical isomerism, optical isomerism. In case of structural isomerism, you have ionization isomerism, hydration isomerism, coordination isomerism, linkage, ligand and coordination position isomerism. So now let's look at it one by one. So if you have ionization isomerism, so what happens is, basically look at the example, guys. See, look at the example. Here CONH3 5SO4 NO3. Can we notice that NO3 can also get inside? NO3 is a potential ligand, isn't it? NO3 is a potential ligand, correct? So because it is a potential ligand, that means that there is a possibility that that can come inside the coordination entity and SO4 will be kicked out of the coordination entity. So that, my dear student, is called as your ionization isomerism. Krishna, where are you going? Why are you going? Why are you going? Don't go. I'm here still. Do not go. No, no, no. No, no. Stay here. Why are you going? I'm teaching you from that time. Now you will leave me. Acha. So if I'm suddenly hungry, I should also leave the class. I'll be like, okay, bye. It's evening time. Chai ka time hai, so I will go. Should I also do that? Okay, tomorrow I will also do. Lunch time means I will go. I will also leave the class. Very nice. Very nice. Okay, next guys, hydration isomerism. Hydration isomerism, my dear student, if you can see, the amount, the number of water molecule inside, the number of water molecule inside the coordination entity, that may change. For example, here you see that there is 0 water molecule in the coordination entity, right? But here you see there is 1 water molecule in the coordination entity. Yes, that is called as your hydration isomerism. Coordination isomerism, everybody see, CuNH3 4PtCl4. If we interchange, it becomes coordination isomerism. C. Now what we have done, PtNH3 4 CuCl4. So Cu went and got linked with Cl and platinum got linked with amine. Got it? Yes, everybody? Well done. Next is linkage isomerism. When do you have linkage isomerism? When you have an ambidentate ligand. Okay? When you have an ambidentate ligand, at that time you have linkage isomerism. Okay? What is ligand isomerism? Ligand isomerism is when coordination compound which have the same stoichiometric composition and same molecular formula but different connectivities with the ligand, and that is different. For example, you have COC. What is this TN2 and PN2? One second. Acha. So CO, this is what? This is diamine propane. Okay, this is diamine propane. So we are writing it as, it should be DN actually. Diamine propane, so DN. Alright. And here, if you have diamine propane, let's say C. Okay. Oh, that is why they are writing 2. See. If the propane, if propane is connected as 1,3-diamine propane, then you write it as Tn. If it is 1,2-diamine propane, then you are writing it as Pn. So understanding, this is called as your ligand isomerism. Okay, this is called as ligand isomerism. And last but not the least, you also have something called as coordination position. I do not think that will come in your exam. This is mostly for your this is mostly for your, what do you call it, JEE. Yes. Now here is another cheat sheet, guys. This is your stereoisomerism. One thing everybody, guys, all the students who want 100 on 100 in chemistry, if you want 100 and 100 in isomerism, this is your cheat sheet. Keep it right in front of you. Every single day for the next 3 days, keep looking at it. Here is your formula, here is coordination number, and here is the number of geometrical isomerism that is possible. All right, yes everybody, please print it out, keep it in front of your face every single day, read it, and that is how you're going to complete it. Okay, finally guys, one last topic that we have to study, it is called as metal carbonyl synergic bonding. Okay, we have something called as metal carbonyl synergic bonding. This I'm going to tell you all right now. Okay, so what happens is everybody, okay, let us understand this. This is very simple, very easy, not going to take you much time, but try and understand this a little better. Okay, so this bonding happens in metal carbonyls. It is called as back bonding, it is called as synergic bonding, it is called as pi bonding. Okay, all right, there are several different names for it, but basically it is just one thing, that it is actually a pi bonding that is happening. Okay, it is a pi bonding that is happening. So imagine that I have a metal. Okay, now the metal has orbitals like this. It has orbitals like this, let's say. Okay, all right, and let's say that I have a carbonyl, that is C double bond O. Now this also has orbitals, correct? Yes everybody, yes guys. Now what happens is, so this, the carbon here had electrons, yes, and that was donated to the metal like this. When this was donated, this is called as a sigma bond. Whenever this was donated, we will call this to be as a sigma bond, right? The first bond that is formed, a single bond, that is a sigma bond. Yes, absolutely. Now the moment the metal has taken the electron, the metal now says that, this carbonyl, it has given me the electron, but it has empty orbitals. It has empty orbitals. So the metal now becomes very kind. And the metal, what it does is, the electrons, it will again donate it back to the carbonyl. What will it do? It will donate it back to the carbonyl, and this time it forms a pi bond. Now it becomes stronger. So it has a sigma bond and it has a back bonding pi bond. And this creates a synergy. Like every time the ligand gives 2 electrons, the metal puts it up, and then it says that, but you have an empty shell, so it gives it back again. Again the ligand has given the 2 electrons. Again it says that, but you have 2 electrons, but you have two empty rooms. Again it will give it back. So what is happening here? A synergy is created, right? A synergy is created here. From here to here, electrons are coming. From here to here, back again the electrons are going. This is called as the synergy. This is called as back bonding. This is called as the metal carbonyl synergic bonding. All right, everybody. Yes, guys. Are we done with this? We are almost done with this. Last but not the least, let us do some previous year question, everybody. Okay? Let us do some previous year question. And by the way, everybody, one last thing that you have to study is Werner's theory. Please study Werner's theory, okay? Please do study Werner's theory from your NCERT book, and I think you will be able to answer almost everything from your book, okay? All right, everybody, this is clear? All right. Now, when 0.1 mole COCl3 NH35 is treated with excess of AgNO3, 0.2 mole of AgCl are obtained, and the conductivity of solution will correspond to, guys, the moment you see 0.2 here, 0.2 means that there will have to be 2 moles of Cl, right? 2 moles of Cl, and that means that directly you can answer it is going to be 1:2 electrolyte. Okay, 1:2 electrolyte. All right, everybody, got it? Clear? Next question. The correct IUPAC name of PTNH32Cl2, everybody. What is it? PTNH32Cl2. It has to be diamine dichlorido platinum, and then if you find the oxidation number, what is it going to be? What is it going to be? The oxidation number of platinum, guys. The oxidation number of platinum, everybody. Rear, please study Werner theory. The first few pages of coordination compound, Werner theory. Yes, what is your doubt? I know you're going to ask me something very stupid. I know it very well. But yeah, still ask. 2. Very good. Yes, the oxidation state is 2. So option A is your correct answer. See guys, these are the kind of questions that will come for 1 markers from inorganic chemistry. Isn't it very easy? It is very easy, isn't it? Yes. So these are the questions that we have already done, and here are some practice questions that you can go through, everybody. These are all the practice questions that you have. I hope that you will all be able to solve it on your own. Yes? Can you all do this? Explain that first question. मन करता है ना तुम्हें मारू पकड़ के, कुछ नहीं समझ आता है तुम्हें, हाँ? When 0.1 mole COCl3NH35 is treated with AgNO3, 0.2 mole of AgCl. Okay, if you write down the equation here, what will happen? You have COCl3 NH3 5. You are treating this with AgNO3 and you are getting AgCl. If you are taking 0.1 mole of this, you are supposed to get 0.1 mole of this as well. But because in the question right here, it is written here that you are getting 0.2 mole. You are getting 0.2 mole as per the question. Okay. That means that right here, everybody, you will have to have your coordination complex will be CONH35Cl, and here it will be Cl2. So from here, because you have 2 chlorine atom that is outside, these two are going to form, these two are going to form you 0.2. Still don't understand here, guys? Check it out. Wait, I'll tell you the page number of coordination compound. What you have to read. You don't have to explain anything. This shows that you guys have basically not studied anything at all, right? This is the page number. See, 1 mole of COCl3.6NH3 yellow gives 3 mole of AgCl, right? Yes, 1 mole of COCl3.5NH3 gives 2 mole of AgCl. 1 mole of COCl3.4NH3 gives you 1 mole AgCl. This is what you have to study. This is your Werner's theory of coordination compound. Read through it. You will be able to understand. It's a very easy, yes, it's a very, very, very easy part of the chapter, and you will be able to do it. Yes, told you, you will ask me something stupid. What is the lesson? What are we learning right now? Inorganic chemistry. The question that you are asking, is it from inorganic chemistry? Is it from inorganic chemistry? Huh? But Chumma, you have to disturb the class, right? You definitely have to disturb the class by doing something, right? Of course, you will not understand. What is the class going on? Nothing. No regard at all for what the teacher is teaching. You will come, ask your doubts, and rafa dafa, gone. Hai na? No, I will not answer that now. Yes, this is the example of secondary and primary valency. Absolutely. Now see where the question has been asked from here. See, the question is formulation of cobalt chloride ammonia complexes. Rear, do you notice this? Do you notice this? See, COCl NH3 2 Cl minus, it will be 1:2 electrolyte. What is this reaction? See, these observations together with the result of conductivity measurements in solution can be explained if 6 groups in all either chloride ions or ammonia molecules or both remain bonded to the cobalt ion during the reaction. Yes, Werner proposed the term secondary valency for the number of groups bound directly to the metal atom. In each of these examples, the secondary valencies were 6. Yes, yes, everybody. Right, everybody. Correct. Guys, do you understand this? Guys, do you understand this, everyone? Yes. So Werner said these few things. Werner said 4 postulates. He said that in coordination compound, metal shows 2 types of linkages. One is primary, which is basically the counter ions, and the secondary valency, which is your ligands. Okay. The primary valency are normally ionizable, that means they are counter ions. The secondary valency, they are non-ionizable, that means they are inside the coordination entity. That means they are inside the coordination entity. The ions groups bound by the secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination number. That means the coordination entity has different spatial arrangement. In the space, it is arranged differently. This may come for 1 mark. Yes. Solvate and hydration isomerism are same. Yes. Solvate and hydration isomerism are same. Yes, Prabhu, what is your doubt? Yes? Got it? So this is your Werner theory. I thought it was very easy. I thought you must have studied. That's why I skipped it. But looks like you guys haven't even touched your book. Yes, guys. Are we done with coordination compound? Any other doubt related to coordination compound? We are done with stability. We are done with synergic bonding. We are done with Werner's theory. We are done with valence bond theory. We are done with crystal field theory. We are done with the understanding of why there is not T2G and EG present in tetrahedral complexes. We understand the splitting of complexes. Right? Is everything clear, guys, for you all? And I'm going to send you the PDF in the Telegram channel. In fact, right away I'm going to do it. Right away I'm going to do it, everybody. You will see that right away I'm sending it in Telegram channel. I need you all to practice the question. Will you all please practice the question? Promise me you will do it. I literally am standing for 5 or 6 hours. If you cannot do this, then all my hard work is gone in vain. Will you please, please, please practice the question, guys? Sending it right here, everybody. Here is the PDF of coordination compound and DNF block. Yes. All right. It is right here. Okay. Thank you so much, Krishna. Now, everybody, tomorrow, 12 p.m., there will be physical chemistry class. Tomorrow, 12 p.m., there will be physical chemistry class. After the physical chemistry class, you will be starting with your organic chemistry class by Durgesh Nandini ma'am. And if your organic chemistry is over, only then tomorrow we will be having a sample paper discussion. If not, if it is not over, then we will do the sample paper discussion on Sunday. Sunday morning, I'll be taking care of your sample paper discussion, as well as I will be sharing some very interesting tips and tricks about how to present your paper and how to get more marks. So guys, will you all be here? Will you all support me? I require the exact same amount of support that you showed me today when we started the class. There were more than 500 students and I want that support, everybody. Okay? With this note, guys, today I'm gonna go and rest now, everyone. I'll see you tomorrow. But promise me you will go through your NCERT book right now and you will absolutely go through the in-text question and the examples. By the way, I have also shared NCERT line by line, fill in the blanks in the Telegram channel. Watch that also. Okay? Watch that also. Okay, guys. With this note, tada, bye-bye. I'll see you all tomorrow. All the very best and study well. Please study well. Okay? 75